So good morning all. Today we are starting with the day 3 session. Today the first session will be delivered by Dr. Aditya Dalakoti sir. Before starting the session, there is an important announcement for all the participants. I request you to please note that yesterday, due to some technical issue, we were not able to continue with the hands-on session. So today the class will be extended up to 2:30 p.m. So I request you all to please stay connected. The details are already uploaded in the drive link of the notification. Today we will upload in few minutes one document which will be required for today's session. So after 20 minutes, I request you to please check the drive link. The detail will be provided there in the drive link. You download the file because it will be required in the session. So with this, we would like to invite Aditya sir to please start with the session. Sir, please.
Hello. Thank you, ma'am. Good morning, everyone. I hope everyone is good. So I see that the attendee list is increasing as we speak. So I'll briefly overview what is the agenda for today, how it links with yesterday, and what is the general plan. So there were some more simulation aspects planned. What I have planned is to, some of you are still facing simulator setup issue. I've noticed in the WhatsApp, but most of you are actually all more than 90% are able to actually get CPP sim running. There are usually issues in CPP sim when sometimes there is a 32-bit to 64-bit compatibility issue. So even that you are supposed to run in VirtualBox or something. Mostly anyone who is facing an issue has not been able to install it correctly. So I request you all to go back to the installation guide and do a new clean installation of it. Apart from that, I think most everyone is able to do it correctly. So there are, as I mentioned, there are certain simulation aspects which are pending, which we will come back to. I want Puneet's, yesterday there was a Puneet's lesson on IO files planned. I would have liked that to have happened before I proceed with the rest of them. So today that session will be done, and then tomorrow I will continue with the leftover simulation aspects. But in the meantime, what I'll do is I will continue with the synthesis aspects. So in terms of the course plan, if I go, if we are moving along, we are over here. So basically, in the timing constraints and synthesis, that's what we are trying to tackle. Then parallel, there'll be classes about IO files. All of these sessions are essentially hands-on sessions because from the perspective of everything will be done and taught using hands-on tools. So there is no one particular hands-on session. Every session is going to be hands-on with respect to the tools. So if we follow along that path, we had requested a while in the first session for you guys to have some kind of Linux environment installed at your end. So I'm not talking about OpenLane, which was there in the guide, a Linux environment. So is there anyone who doesn't have a Linux environment? And if so, why not have a Linux environment? I would be curious to know. And if everyone has a Linux environment, then we are good to go to proceed on that direction on today's session. I'll wait for like a couple of minutes to see if anyone responds with something. Basically, in order to proceed and actively participate in this course, you should have a Linux environment. If you don't have a Linux environment, you need to put a VirtualBox in and install a Linux environment. There is still time to do that because today's session, there'll be all very less and there'll be only Yosys work involved. But in following sessions, the extensive use of the Linux environment, that is pretty much the only thing we are going to be doing. So I request you again to please install Linux either in VirtualBox or directly. Otherwise, you're not going to be able to do anything. Okay, I don't see anything in the Q&A. So I'm assuming everyone has a Linux environment. And as I mentioned, we'll come back to certain simulation aspects after each session on IO files has been completed. So because of yesterday's technical difficulties, we actually restructured it a little bit. So everything is structured well and together. Now, in terms of timing constraints and synthesis, the tool which we are going to be using is Yosys. What I'll do is I will request everyone to open their Linux environment and try to type Yosys. If you get this window, it is fine. If you do not get this window, if you do not have Yosys installed, I would ask you to do sudo apt-get install Yosys. This. So for me, since it's already installed, that is why it is showing installed. So till now, I have never requested you to install this. So please go ahead and install this. This is like a couple of minutes thing, so it just runs in the background. That's why this was never given in the previous guides. So please, please install Yosys in your Linux environment if you have not done so already. Anyone has any issues doing it, please let me know. Yeah, sure, Trish. This is as I said, the way the lecture is planned. I'm just telling you to install it now. We'll let it install in the background, and then I'll proceed with some aspects of the synthesis lecture, and then we'll come back to the Yosys environment and play around in that environment. So that's all fine. Don't worry. You can install, as I'm mentioning, please install Yosys in the background. And as I mentioned again, since the attendees are still joining, the way we'll proceed with today's lecture is we'll first go into the synthesis aspects, and then once Puneet has been able to do the IO files lecture, then we'll circle back on some of the missing simulation aspects, because those are important to be linked using some of the IO files aspects he'll teach now. So that's the general plan. So again, Yosys, Komal might be able to run in the native Linux of Windows. I'm not sure. Even if you can, you'll not be able to do the rest of the OpenLane framework. So I would advise you to have Linux installed. Amrutha, there is no, you have to just type this or any other command to install things in your whatever. If you're don't have Ubuntu, whichever Linux environment you have, there are commands to install. So that's all. There is no other step for installation. Just one command. In Fedora, it's not apt-get. Ashley, in Fedora, there is an equivalent. Vinod, in order to install Linux, you need to install VirtualBox, and you need to put Linux in VirtualBox if you are working in Windows. And that is not something which you can pull off during this time. Hence, we requested that all to be done already for the weekend, previous weekend. If you have not done that, please do that after today's session. Put VirtualBox in your machine and install. Okay. Yes, okay. So the idea is this: if you put Linux in VirtualBox, then rest everything you can do. Malikarjun is saying there is some error. So when do you get this error? Naveen, today Docker is not needed. Today only Yosys is needed in today's session. Okay. So Malikarjun, this you are getting this error lock on the front end. This is when you are trying to, you guys are trying to run Yosys, or this is when you're trying to Gangadhar and Malikarjun, this is when you try to run Yosys, or this is when you try to install Yosys? Lakshmi will come back to those packages. A Docker is not needed without you for Yosys. Yes, Naveen, that is sufficient. Okay. I would advise you to keep working in the background to try to install Yosys, and then now we'll proceed with the lecture. Sure, Divya, you can use that if you have a Linux environment on that. Okay. Now, try to sort out this Yosys installation. Basically, it's a quite straightforward and simple tool, which is quite easily available. So the general goal is to install Yosys. That's the only thing needed for today's session. Okay, so now that you guys are doing that in the background as well, the agenda for today's first session is to be able to explain you what are the SOC level timing constraints, why are they important, where do they come into the picture. We will look at some of them in today's session. We will start with small examples of what synthesis means, what does it do, where does it come into the picture, what all things are actually done in the process of synthesis. And Yosys actually gives a very good examples for uh, steps and optimization procedures for that. But before we go into deep dive into that, I actually wanted to give you a bigger overview picture so that you are able to appreciate the whole area. And then with this specific tool and with this specific environment, we can target only few things, so which we'll actually be able to do, and that's what we'll do. So we'll continue. So the general aspects of next couple of sessions is that we'll try to tackle the timing constraints with respect to input, output delay, and environmental attributes. These are some of the constraints which will be also taken up by Puneet in his STA lectures, where he'll use OpenSTA and use these constraints to further evaluate and show you how they come about in timing analysis. From the aspects of synthesis, we'll go into the extensive use of synthesis tools with respect to Yosys today. Okay, so what do we mean by SOC level constraints? So if we have some block which looks like this, so let's try to appreciate the complexity of this block. And just for your information, I will show a lot more detailed constraints within the time bounds of this session. It's not possible to go into all possible constraints. We will try to go into the basic ones which are necessary for to be able to set up any SOC. Okay, so when we have SOCs, right, we have multiple analog blocks which are communicating to multiple digital blocks. And then there are multiple digital blocks which are communicating with each other. There are also memory blocks which are communicating with digital blocks. They might also be communicating with analog blocks. If this is the top level view, then there might be multiple clocks which are coming from off chip for you. Apart from that, what might be the case is you might be working in different hierarchies. So I'm saying this digital block and this digital block is currently a current design. So you might be working at the top level hierarchy, or you might be working at a block level hierarchy, depending on what block you are trying to get through your implementation flow at that moment. So it is very important to be able to understand the constraints which come up at different level of hierarchies, and why they are important at that level of hierarchy, to be able to understand that the major constraints which are important are input and output delays. People are always confused on what to take their values as, which of when to set of which one of them. That is why we wanted to clarify the input output delay aspects very carefully and nicely during the course of this this workshop. Then there might be signals directly coming into the digital box. So if we go a little bit further, there might be clocks which are then going into the digital blocks and passing through, say, divided logic, and then going into different blocks. So anyone has any doubts over what I'm trying? Anyone is lost in terms of this this picture I'm presenting here, or has any questions? Please feel free to ask right now. Okay, I'll wait for a minute to see if anyone has any questions, and then I'll continue with the further explanation. The way you can use VMware as long as you have Linux installed on it. Okay. So no particular questions with respect to this slide. Shubham, we'll come back to that. As I mentioned, there are certain aspects of IO files which we'll talk about, and then we'll come back to some of the missing simulation aspects. So in general, in order to give you a brief overview, from CPP sim, we observed that loading and transition time have effects. And during the implementation flow, it is important to realize that all the sizing, all the interconnects, how do we build models for that? And in order to build models for that, we need to have a simulation platform that is used. You pass all possible iterations, and when Puneet shows you the lib file, you'll observe that there are different matrices for different rise time and transition times. And then that's why I'm saying we'll come back to the that work once we are done with the some of the IO files aspects. So we want to have a full circle loop there, and that's why we'll come back to it. So I'll give you this. Naveen, we'll come back to your question. Lakshmi is asking, where did we get in clock C? The clock C and clock A are off-chip clocks. So you can have multiple, there is no particular reason to believe that you have a single off-chip clock. You can have multiple off-chip clocks, which are maybe synchronized off-chip, or they might be completely asynchronous to each other. Is that clear, Lakshmi? Okay, I am assuming that's clear. It doesn't have to be a block. It can be they can be coming from off chip completely. So Naveen Cabra is asking about voice. Can someone confirm from the E&ICT side if my voice is clear today, or is there issues today also, or are there issues today also? Or Puneet, I see Puneet there, or can Puneet confirm regarding the voice? So Komal is confirming that I'm audible. So I guess the issue is gone. So I would request you to check at your end, Naveen. Okay, so students, most of the students are today hearing it clearly, so that is good. Perfect. Thank you all the participants. Now, moving along on the same discussion front, there might be, for example, there might be signals like control data which are completely asynchronous to the clock, and there might be these data signals which are completely asynchronous to the clock. Similarly, even though these signals are completely asynchronous to the clock, you have to be still worried about the capacitances. These capacitances can originate due to wires. These capacitances can originate due to the gate sizes. And this is one of the reasons we made you visualize in yesterday's session using CPP sim simulation that wire load, capacitor load, all wires are capacitors and resistors. The gate sizes, everything matters. So if till you visualize it with your own eyes, it is obvious. Everyone has this doubt. Okay, why are we putting a capacitor here? Because all wires are RC, and as soon as you put an RC on any gate, your loading is leads to rise time changes. Rise time changes lead to delay, which we observed yesterday. So it's important for you to realize that these environmental attributes are still important to be put in. Now, you can have conditions like your input data is on clock B, your output data is on clock C, which can be which can have different relationships with each other. We'll not go into too much detail on these, but wanted to point that out for the particularly with respect to this course. We want to stick to explaining the SOC and hierarchical aspects of input and output delay. This is input and output delay are one of the most important things which people do not realize. How different levels of hierarchies in an SOC they work out, and everyone is always confused. Okay, should I put input delay here, or should I put input delay at the hierarchy level? You need to be clear which hierarchy level you're working on, and that is what we'll try to clarify as we try to go through multiple RISC-V IPs in the course of this design. Okay, any questions on this? And also there might be multi-cycle paths from the memory basically. So this is the complexity of an overall SOC level constraint. And I hope you are able to visualize why synthesis and timing constraints is such a big deal. And we will try to take a stab at part of this problem. The idea is to make you understand from basics very clearly some basic constraints so that you are able to use those things well. Okay. Then there is another aspect of the design. Before we go into this, I think Firoza ma'am from IICT Academy said that there'll be a file uploaded in the drive. So there was a zip file which was provided, and it should be in today's folder. It has some examples which we will be using for synthesis using Yosys. In the background, I advise everyone to go to your drive folders and please download those files. I repeat, please in the background, go to your drive, download the zip file which has the synthesis examples in it. It is in your drive folder, which you have got the link from E&ICT Academy. Please go and download that. After a few slides, we will start using those examples. Okay. Now, as you're doing that in the background, what we'll do is we will then further go on appreciating the aspects of why timing optimization is important. Now, the reason I bring this topic up before hand itself is so a lot of times participants or students or even researchers have questions. How do we even make use of the open source tools to do synthesis if there are hardly any optimization features available in the tools? So my general notion there is, as long as you understand what timing optimization for synthesis means, what all different optimizations are needed or are done by tools or should be done in the tool to optimize and meet your timing. And for most real world applications, that is not very hard. So the most real world applications can be done quite slow. So, but in general, so as long as you know what all timing optimizations to do, you can actually restructure your RTL in a way so that your tool doesn't need to work very hard. You do not need to just always, so a very simple example of that is you don't need to just write C is equal to A plus B. And both A and B are, say, 32-bit registers. If you write C is equal to A plus B, then what kind of adder is to be implemented by the tool has all the freedom. And if you give tool all the freedom in open source tools, obviously it will not be able to do the best adder implementation. But if you go and specify how bit by bit the particular adder is implemented using whether a carry skip method, carry save method, Wallace tree method, whichever method you want, then you have already done the actual optimization yourself, and you can still use the open source tools to further do synthesis on it. So please appreciate that understanding of timing optimization concepts is in parallel to the fact that whether or not the tool does it automatically. You can always do synthesis timing optimizations on your own end as a good RTL practice. Okay. So in the meantime, before I proceed, there is there is a good point actually made by Gangadhar here with respect to the technology node. And since I did not ask you guys to install OpenLane yet, what we are going, ma'am, Firoza ma'am, there is actually a file I would like to be uploaded in the drive as well. This is for the technology node file. Since this is not yet installed on their end, I have a folder which I forgot. Please, if you can please upload that as well in parallel. It is needed in today's session. It would be helpful. I'm just sending you an email for that. It would be really
Yeah,
helpful.
sure. Yeah, sure. It will be done within 10 minutes.
Sure, sure. Thank you, ma'am. It slipped my mind that that is also needed. Sorry.
Okay, no issues. Thank you.
Guys, give me just a moment. Let me send the file to Firoza ma'am and we can proceed from there. Okay, sorry. Give me just one moment. I am forwarding a file which I sent to Puneet yesterday. Okay, so EICT. Okay, am I sending it to EICT Academy IIT Guwahati? Okay, perfect. Thank you, ma'am. This is awesome. Thanks, Gangadhar, for pointing that out. That currently, since there is no, I have not requested you to install OpenLane yet, so you do not have the technology file available with you. So there is like a we had actually done this yesterday that we took the technology lib part out of the PDK, and we had created another folder, and I sent it to Puneet. I just forgot to send it to EICT Academy. So I just done that, and you'll have it in the drive in some time, and then you can download it. Okay. It's not immediately needed, but will be needed today, so don't worry about it. It will be uploaded by that time by EICT Academy. Okay. Thank you, everyone. Naveen, let me look into the yesterday's session at the end of today's session, whichever ones you're mentioning, I'll look into that. Okay. So, moving along. So coming back to where we were in the slides, we were saying that we are trying to do synthesis. In order to do synthesis, the two aspects which are most important are timing constraints and doing timing optimization. And with respect to timing constraints, which we'll be dealing at hierarchically with respect to input-output delays. Gangadhar, we are uploading the PDK, which is needed. So then the second aspect, which is most important, is timing optimization. With respect to the synthesis tools, it is not always possible to do a good job at with respect to open source or timing optimization. So the onus falls on you, the RTL designer, to write a good RTL to be able, which is self-optimized. Apart from that, there are certain other good RTL practices which can be followed. For example, if there is a given node is split into multiple nodes, and you know from SOC perspective that there'll be high load on this, you can split it from the driver side itself. There are arithmetic optimizations which are possible. We'll dive into some of these aspects also. We'll give you an overview in the today or tomorrow's session, just to have you understanding. But there, I also wanted to give you, in terms of actual timing optimizations, there are a lot of them, like adaptive retiming, boundary optimization, register application, which are not really possible in uh, doing automatically in this tool environment. But I wanted to let you know that there are a lot more possibilities. Some of them we'll try to get into, but will not be able to get into all of them within the constraints of this course. Now, as we move along, Gangadhar is pointing out that library files are open or need to take from a Oh, Gangadhar, we'll be using Sky 130 models for any implementation flow work, which are openly available on the internet. So we are not asking you to do an NDA on this. So this is the openly available PDK. Does that answer? Okay, perfect. Sorry for that confusion, but yeah, that made me realize that I have not sent that to the participants yet. Thank you. Now, before we start to dive into some of the synthesis examples which I have sent around today, which you have downloaded probably in the background, I wanted everyone to understand what do different design objects mean, because they'll be very important to be able to visualize hierarchically different designs. So just wanted to give you a brief overview on design objects before we go and jump into the tool environment. Okay. Any questions up till now with respect to the why timing constraints, why optimization and all that is important? Okay, so design objects. What do the different design objects mean? So design objects can be a design, it can be clocks, it can be pins, it can be ports, it can be nets, it can be cells. So all of these are different design objects which are very important to be understood and to be visualized when we are actually working on any implementation flow. So we will look at these one by one in an example to be able to better understand it. A lot of you are used to writing codes in Verilog. So if we take an example in Verilog, if we have, say, a module full adder. Now in this module full adder, this full adder is a design object called design. And if we follow along, if we have multiple inputs A, B, C, and clock, the different and outputs fsum and fcarry out, A, B, C clock and fsum fcarry out are design object called ports. Then if we move along, we have the way this full adder is implemented is using two half adders. Then each of these half adders, which were design objects in their own hierarchy, are now cells in this hierarchy of full adder. And then we might have encoder, which is within another hierarchy, which might have pins, which are called from different instances. Sorry. So if you call encoder as an instance, and if you connect it using different connect by reference, then there are pins and they are connected through wires or nets. So is everyone clear on this? We'll take an example of the same through actual visual representation as well. I'll first take that example and then see if anyone has any issues understanding the different design objects, because these are actually quite important. And whether you work with professional tools or whether commercial tools or open source tools, it is very important to be able to distinguish between these, whether it's a port or a pin, whether it's a design or a cell, whether it's a pin or a net. It is very important to be able to visualize these. Now, design objects, if we take the same example with respect to a block view, so if we have these full adder, same example as last time. So these A, B, C clock, fsum, fcarry out, these are ports. Half adder, two instances of these. They are connected through wires called nets. Individual A, B, half sum, half carry. What are these? These are they have pins. Okay, these are pins of the instance which are then connected through nets at the top level of hierarchy. So pins are connected through nets, and at the top level hierarchy, the input outputs are called ports, and individual instances are called cells. So half headers are cells, at the top it's a design full header. I hope everyone understands the context of design objects, since this will be important when we are visualizing certain examples using Yosys. If anyone has any doubts, please let me know. I hope everyone has written some. Okay, Wasim, I'll get to pin some Verilog or other in their lifetime. So I was able to appreciate this. So Wasim, pin is, so if you instantiate multiple, if we instantiate multiple, half adders, then in the port of the half adder, which if you just create a half adder, it has ports then, but if you instantiate at the full adder design level, then it becomes pins. So because at the hierarchy of full adder, these are instances or cells, and their ports are now pins. It depends on which hierarchy level we are. Okay. Nets are what are connecting these different ports and pins. Why do I need a combination? So I have not given you the definition of the half header. We can have a sampling at the end. No one has restricted us to anything, so you can always have a clock to sample. Okay, so moving along. Ports versus pins, which is the question of Wasim as well. I wanted to emphasize in a separate slide. So input and outputs of current design are ports. They become pins if current design is instantiated in other parent design. For example, if we have two designs, first and second, these are FI and FOR ports, in and out are pins. Now, if this is the first is instantiated in third, then FI and FO will become pins, and TI and TO are now ports at the top level of the hierarchy. When you instantiate something, okay, instance and cells. So the instance names are called cells, basically. Okay, good questions. Nice. People are understanding. Design hierarchies, very nice. Again, if we have pins, input and outputs of a cell instantiated in current design, they become ports if the cell becomes current design. Let's take an example. We have first, which is instantiated inside third. It has pins FI and FO in this hierarchy. But if you take just first, then FI and FO become ports. So please appreciate from the SOC perspective which hierarchy you are working on. Depending on which hierarchy you are working on, it might be a pin or a port. And similarly, later on, we'll look at input and output delays. And it is important to understand which one is important where. Are you at the top level hierarchy, or are you at a slice level hierarchy, or you are at some inside hierarchy, you're optimizing the design. It is very important to visualize that, and input output delays changes with respect to where your ports are associated with. So please understand that you always have a hierarchical design, and it is important to us understand different design objects within that hierarchical design nice and cleanly. Okay. One last topic I would like to cover before we switch into Yosys environment for the last 1 hour of this course is library objects. So Puneet will go more in detail into this, but similar to your design, there is also a library or lib file, and it's based on its description. You can call it from the tool environment as well, and it is also referred using the as objects. There are library names, there are library cells, and then there are file names. So in tool environments, everything is referenced as objects, and that is what I wanted to explain here. We will look at an example later on in the tool environment where this becomes important, but before that, we would like the IO files lecture to have completed. So we'll get into more detail into this in a later session. Now, this is all setting the background, diving into synthesis. So what we are trying to do, we are trying to do synthesis implementation flow. In order to do synthesis implementation flow, for an SOC, we need to be able to understand the design hierarchy of a SOC. Okay, that is point number one. Point number two is you need to understand that timing constraints play a very critical role during synthesis. Point number three, timing optimization techniques. There is a misconception that if you're using open source tools, you cannot do anything. When you are using open source tools, you can do complete synthesis with an optimized design as well if you are, but the effort then needs to fall on the RTL design perspective, and it leads you to write a very better RTL than you very lousy RTL, which you let the commercial tools handle. So that is the perspective I wanted to bring about. So this is again the same slide which we discussed in the last session, but I wanted to bring to your attention just one point here. So we talked about this yesterday with respect to the levels of abstraction of simulation. Similarly, there are levels of abstraction of design as well, and they are it's the same slide. They're from system level to high level to behavioral to RTL to logic gate to physical gate to switch. It is the same thing. The point which I'm trying to make here, the box bounded in green, this is where our target of synthesis lies. And even this is where the target of the implementation flow in general lies. So this is where we are targeting. And in order to target this, you need models and IO files which are compatible, which can be run in fast time, which we were trying to visualize. How do we create such files from transistor level models so that they run fast? Because in actual, we design everything using transistors. So everything is actually designed here. But we saw yesterday that the transistor level models are huge and complex. And if we go about running those and do an implementation flow, it will take us forever to do a simple designs implementation flow. So we abstracted our models in terms of delays, which we'll look into STA. And in order to do that, you need to visualize that what is important. Your capacitor loads, your RC loads, and your transition time is important, which we'll see in the lib files. Now, with that perspective in mind, I would like, I'll get rid of these slides now. I'll put them on the other side. We'll try to go into the Yosys environment. So I installed, I gave you guys PDK. I hope it is already in the, drive, and it's not needed as of now, but as soon as it shows up in the drive, I request you all to please go and download that as well. Apart from that, there is, there was already examples, synthesis examples loaded in the drive, which I hope you have already downloaded. Now, in order to run today's lab sessions, the only aspect which is needed is Yosys. So don't worry about don't worry about the open lane aspects. you still have time to get the installation done correctly. Currently, we'll only target the synthesis using Yosys, and we will need the examples in your Ubuntu environment where you have the Samarth is correct. We need the examples in the Ubuntu environment. You can, if you are working on virtual box, you can transfer it. Basically, you need to have everything in the environment you're working on. So let's see. Let me try to make it a little bit bigger. Yes, I am zooming in. I get that. Okay, 20. That should be a little bit better, I hope. Let's see if that works. Okay, I hope everyone is able to now see the screen with respect to the Zoom issue. Okay. Now, if I go into this directory, what I've sent you guys is this. There are a few examples, example 1, 2, 4, and 5, which we will like to go through and visualize using Yosys. I hope you already have the examples in the Ubuntu environment, which as Samarth was pointing out, if you don't, I would give you now a couple of minutes or few minutes to transfer and copy and paste these examples in your Linux environment, and then we'll start from there. So take a couple of minutes, have a directory in your Linux environment with the examples which are uploaded in the drive, and also if the PDK part. So the PDK part, let me give you tell you what is being uploaded in the drive. So in the drive, which you will have is something which looks like this. It's called Sky130A, and it has libs.tech and libs.ref, and we will be using those. And so I hope it's there, or if it's not there, it will be there soon. Please download this Sky130 and put it in your Ubuntu environment as well. So in terms of the lib files, we'll be using this, where did that go? Libs.ref. Lib. Yeah, so we'll be using lib files from here today in the Linux environment. So please put this Sky130A library, and then the rest will follow later on as we proceed through the course. So try to do two things in 2-3 minutes. Try to copy. The library is a little bit big. It will take some time to download, put it in the background to download, but try to download the examples and put them in your Linux directory. And they'll look something like this. This is what you should have essentially. Take a couple of minutes, please do this. Naveen, virtual blocks, there is just one virtual box is pretty straightforward. It's a freely available tool. So I'm not asking you to go and pay for anything. VirtualBox is a freely Oracle VirtualBox is freely available. Okay, Rishabh is asking how to install library. Which library, Rishabh? This library this has been uploaded by E&ICT in the drive. Just copy it into your Linux environment. So I am hoping people have these examples in their environment. Yes, synthesis examples for Verilog file. These are very simple Verilog files. Those are what need to, yeah, okay, this don't have this. Let's remove this thing. So you should have these 4 files. Absolutely. Yes, you will need to have Ubuntu ISO. Ubuntu ISOs are easily available. That's for Vinod. Okay, now proceeding into the example. As someone is asking, can you show more? So these are very simple examples. Don't worry. We'll go into the more complex ones later. First, wanted to help you visualize what is meant by not CD more. Different. I want everyone to be able to visualize the I want everyone to be able to visualize different aspects of synthesis well before we actually proceed to complex synthesis. Okay. Now, here's what we are going to do. We are going to do a read Verilog. So read Verilog. No, sorry, my bad. We're going to type Yosys. So as soon as you type Yosys, please type it in the directory, where you have these examples placed. So for example, I typed it in the directory where I had example 1, 2, 4, and 5. It will be easier for you to reference them and not put their paths in. So what we are going to do is we are going to do read Verilog. And then we are going to say example 1. And let's see. What did it say? It said parsing Verilog input example 1 to AST representation, generating RTL representation for module latch. So successfully finished Verilog frontend. So this is the answer which you should get when you say read Verilog, example 1.v. So the question is, what does all this mean? Parsing Verilog. So typically in synthesis, what happens is synthesis has multiple stages of the flow. So design is converted into one form of representation to another form of representation as you follow along in different stages of synthesis. So the form of representations vary with respect to different tools. And here it has changed it to AST representation to RTL, IL representation. The exact names are not important, but what is important for us to realize what we are trying to do. So you have certain RTL and you are trying to change it into a gate level netlist at the end of the day. So the tool does it in different stages. It converts it into a more easily understandable form of it. Then it goes and maps it into different design libraries, which we'll see as we proceed through the different aspects of this design flow in synthesis. What is more important, what is also important here is to be able to visualize how do we understand and see what is going on in behind, right? So what we can do is we can do something called show, and we can say latch. So because it has already passed a module latch, which was inside example 1, we can now actually run a show on it, and you will get something which looks like this. So are you guys able to get something which looks like this? Before we proceed into explaining what is going on here, I would like everyone to type Yosys, type read Verilog example 1, then do a show latch. Awesome, Malikarjun, very nice. Awesome, Shreyas, nice. So I'll give a couple of minutes to everyone to just catch up. In the meantime, I would like to explain why we are going from so much basics. So in order to do these implementation flows on RISC cores, it is very easy. So you can just pick up a core. There are already set up scripts. You can just run them and you can say, okay, we have done a RISC core implementation. That is useless for you if you actually want to do it on any real design, or if you do a design iteration on any existing RISC core. It's all useless until and unless you do not understand how the scripts are set up, how the background files are getting set up, how do we modify them if we do change something. That is what is important. So you need to understand what is happening in each and every part of the flow, and what happens in synthesis, what happens in backend flow. So once you get that, then you can set up anything you want. So we'll take examples using RISC cores. Before we do that, we want to take very basic examples to understand. So I hope everyone is able to see this dot view. So what is happening here is we are calling a process. It would be, yes, Pradyum, you need to be in the same library. Otherwise, here instead of example.1 or p, you need to pass the complete path. So it would be easier for you if you are in the same library itself. Okay. So if you are able to see this, then let's try to understand what's going on over here. Data and enable are going into example 1. Let's see, I think we have example 1 here somewhere. Oh, I'll wait a minute. I'll open another screen for that. Okay, new terminal. Okay. That's project 1. Okay, let's try to compare it to the Verilog. Okay, what did we have in the Verilog? We had enable and data, which are going as inputs to a process in example 1. Now, what happens is it outputs Q, which it outputs. This Q is now supposed to also be able to be passed inside example 1. Now, basically, if enable is high, the interesting thing which we need to understand here is if you are actually trying to do a synthesis, your end goal is to be able to map it into your end goal is to be able to map this into a technology latch, right? You need to make the tool understand that where the module I've written here with these specific input and outputs should go and match some technology library latch. Now, if in this representation, because there is a loop here, it would be very you cannot really isolate different inputs and outputs. So when we do synthesis, it is important to be able to break latches. It's one of the different techniques needed in synthesis, that you need to not have logic loops for the tool to be able to understand that you want to map it to a specific gate library gate. So we'll do again the same thing here, what we did. And let's try to change it a little bit. Okay, now when we do read Verilog, what we'll do is, I hope this doesn't break because I'm reading the same one. Yes, it will. So you will need to actually start Yosys again. That's the finicky part about open source tools. They are very, they don't have override capacities and all that. So let's run this again. Okay, what we'll do is read Verilog. Now this time we'll put a tag no latches. Okay, what is the tag? No latches. Read Verilog no latches example 1. That's what we are going to do. Same thing as last time. It took it from a Verilog to AST representation to RTIL representation. Okay, now what we'll do is we'll do show latch. Now let's see what comes up. What comes up now is this. I hope everyone is able to get this at their end as well. I will wait here for a couple of minutes to for everyone to catch up and try to get this representation. And then we'll try to visualize why this important representation is more important when we are trying to do when we are trying to actually map it to a gate library. Okay, Rajan, basically last time we said, where is, okay, here's the Verilog. Just do a no latches tag before you, after you read Verilog, and then again do show latch, and you should be able to get this. And then I'll explain this in a bit. Vishnuvardhan, yes, good question. It represents a process. We will visualize how the representation of it changes as we follow along in different stages of the synthesis flow in Yosys. It's one of the intermediate representations which Yosys creates. So it's a very good question. It's just an intermediate representation. We'll see as we follow along different stages. Okay, now if everyone is able to get this screen, what we need to understand now is what does what does this represent and compare to the last case we had? In the last case we had, this Q was feeding back into this input module again. Now, understand this from a gate level latch library perspective. So from a gate level latch library perspective, you have a gate so you have a gate in Sky 130. In any PDK, you'll have a latch, right? In that latch, there'll be a data and an enable as an input and a Q as an output. In order for us to match one-on-one, because the next stage in synthesis is matching it to a gate library. So in order to match it, this loop had to be broken, because otherwise this loop internally exists in the logic, but we do not want this in the top level representation. Otherwise, we'll not be able to do our synthesis correctly and the gate matching correctly. That's why what we said was break this loop. That's what we mean by no latches. Break this loop so that we are able to do a correct gate level mapping. Okay. Raj Shekhar is with latch and without latch. It is that's a good question. What we are trying to say here is, because in Verilog you are saying it's a latch representation, right? In Verilog you are defining a latch. So essentially you need to make the tool understand that what you are writing is a latch. For the tool to be able to understand what you're writing is a latch and map it into a gate library, you need to be able to explicitly tell it that break the loops. Anant, yes, we'll look into some other aspects as well. Pradyum, yes, you had a, if we go back to wait, wait. Have a loop. You definitely have a loop. See, if data is going to queue, right, and then basically this is where the loop is getting created. In your Verilog, you have written a loop, and now you need to make the tool visualize that this thing is not a loop, but you need to map it to a gate latch, which is in the technology library. So this is these are all very good questions from the participants, because now you are trying to understand what are the difficulties the tool has to when it tries to do all this, right? When we just type the commands, we don't realize what goes on in the background when the tool is trying to create a synthesis netlist for us. So in order to be able to do different stages of synthesis, one is to break down your RTL into a intermediate form, and that an intermediate form is then mapped into gate level netlist. You need to be able to run this. Yes, no latch is a keyword, Surya. Yes, for sure. Okay, so before we do the rest of the options in the synthesis flow, what we are going to do is visualize a couple of more examples before we do that. Okay, let's try to go on in this pace and try to visualize little more things. Okay, so let's see, what do we have? If we go to the examples directory again, we have something called example 2. In this example 2, if you see what I have written here is, it's an n-bit adder, and n-bit adder is a module. That module then has, there is also a half adder module, and then there is a full adder, which is described using your half adder, which is also described separately. So there are different adder descriptions here in this module. So let's proceed. Okay. Now we want to do the same thing. Let's clear this. If we okay, there is no command and Yosys for clear. Okay. Let's proceed in the same form. We want to do read Verilog. This time we want to read example 2. Since I wrote example 2, I know there are no latches there, so I can avoid the tag. So we want to read example 2 Verilog. So what happened as soon as I read example 2 Verilog, it parsed the Verilog input from example 2V to an AST representation. This is an intermediate representation in the when we do synthesis. Then for all the different modules present inside your example2.v, it created something called RTL representation, which when we do the show command, that is what we are visualizing. Okay. So it created an intermediate representation for different modules in the form of its own terminology called RTL-IL. Now you can actually go and do the same thing as last time, and we can say show. I would ask you to put a command tag called stretch. This helps to put inputs on the left side, outputs on the right side. And now you can actually visualize each one of these. You can say show stretch half header. Something like this will show up. We'll come back onto what this means. Then we do show stretch full header. Where did that go? Okay, it actually cannot show two windows, so I'll actually do this. Zoom to fit, and then I'm actually going to print to file. Just okay. So let's do the half header again and bring that up. So what does a half header do? In half header, there are two inputs, X and Y. They go into a module called AND and then a module called XOR. The modules are then passed through something called buff, and we get output C and S. So you have the intermediate representations for half header. And let me see if I can pull up using Evans the other representation, the documents. Evans output.pdf. Okay, so the other representation, not this, is this. Okay, so this is the full adder representation. So in the full adder, it's not showing completely. Let's see. Okay, so because of WebEx, my system is not behaving well for some reason. So what we'll do is we'll again do the full adder visualization in GraphViz, and we'll see what that does. And then we do zoom to fit. Now in the full adder, what we did was we had inputs X, Y, C in. They pass through AND, XOR gates, and you have your usual full adder netlist, which goes out to C out and S. Typically, everyone knows full adder and half adders what they are. And here I just wanted you to be able to visualize these, how the tool is understanding them. The critical thing for everyone to understand here is how do you make the tool understand? Okay, that's what the tool is right now, understanding your netlist in this form. I will wait for a couple of minutes so that everyone is able to catch up to this point of the example 2 and full header, half header, and stuff like that. I will also try to do a GraphViz representation of this, and I'll keep this up in the screen for now. So we also wrote a module called n-bit adder. So this is how the tool is understanding n-bit adders. It is taking multiple inputs and then it is actually creating intermediate representations for them as well. So whatever you write in Verilog, the tool is able to then map it into intermediate representations, which later on then it will again map into some gate level representations based on as you set it up. The dollar is not propagation delay. The dollar is just where the input is getting connected. We'll come to that. One thing we can do here is let's put width here. So again, every one of these are some thing to do with so different kinds of definitions of input and output ports, and they have different representations. So input output ports are mapped like in this hexagonal representations. They're also mapped in this diamond looking representation. They all have different meanings. I don't want to go too much into RTL IL representation. That's where all that explanation comes from. It is otherwise it will take a long detour explaining all this. I just want everyone to be able to visualize that what you're writing in Verilog is generally what you're getting. Okay. No, Vishnuvardhan, not yet. The size of the gate is not represented. It's just you have different inputs and you're just showing that it's going into different inputs. It's indices 0001. These are all the bit widths which are specified in the n-bit adder representation. What else? Dot file, usually you can just run dot files in the Linux environment. Okay, now, because we have just half an hour left, I want to proceed a little bit forward. What we would like to do is we would like to run Yosys again on another Verilog which we have written, and then observe that following a couple of more stages of the synthesis flow. Right now, the only thing which we have done is we have been able to read the Verilog. That is the only stage we have done. We are reading the Verilog and we are seeing what the tool has interpreted that to be. What's the next stage of the synthesis flow? Let's go and visualize that. Okay. So in order to do that, let's do read Verilog. Let's try it on example 4. So as you can see, the example 4 is a rising HD flip-flop with the asynchronous reset. One of the requirements for to be able to do synthesis is using open source tools is to be able to map your D-type flip-flops well. In order to do that, there is another stage of internal representation which is needed to be passed through. And let's first do show rising this, and we'll see what kind of dot file. Wait, let me do show stretch rising. So essentially what we have now is We have an asynchronous reset. We have a D input clock, and we get Q as an output. Now we want to be able to map it into something which the tool will be able to recognize and map it into a gate level library later on. So we would be doing a few things. We'll call what is called a proc operation, and with the proc we'll do proc ARST, and which what it does essentially is it is able to make the tool break down the D flip-flop and understand that well. So again, if we go and visualize that, let's do this. Actually, there is another thing which we need to do is proc DFF. No, sorry. Okay, my bad. Yosys is a little sensitive this way. So we'll do read Verilog. Let's do read Verilog example 4. And then we'll do proc DFF, proc ARST. One is to able to identify the asynchronous reset. One is to be able to identify the D flip-flops and mark them. Let's go and see show. Let's go and do show rising with a stretch tag so that inputs and outputs are on the other side. And there's actually okay. There's something missing. I need to check what's going on. Let me check. Why is my output not showing up? Give me just a moment. Okay, let's try opt clean. Show rising. It's quite odd. Okay. Usually, let me actually, I have captured what I wanted to show here. I'll come back to the tool and try to see why it's probably creating an intermediate representation which is not working. I'll try to come back and fix it. But in general, I've also captured all of these into commands, in your slides, so you can go back and do them on your own time. So what we are doing is with the proc ARST and proc DFF, we identify the asynchronous resets, we identify flip-flops in the process and convert them into specific representations, which then the tool will be able to map correctly. Okay, and then there is a question which is asking, are these commands stretch show? So these are Yosys internal Yosys commands. Pradyum, the reason for stretch is that your inputs are all on the left side and the outputs are all on the right side. It's easy to create, visualize what is going on in your dot file representation. That's all. Okay, so prior to the proc command, you should have gotten something like this. And after you do a proc, what you'll get is something which looks like this. So if you are able to achieve this or not with the proc, for some reason, it's not giving me the correct graph-based representation, but captured the output before, this is what you should get. So in a given cell, it is then able to map the fact that there is asynchronous reset, that it is a D-type flip-flop in it correctly. So that is what I wanted to show you. So when you are doing synthesis, it is very much important for you to understand, to tell the tool what is a latch, what is a flip-flop. That there, if there is an asynchronous reset, you need to be able to tell the tool to identify that. So typically, if you do go with commercial tools, all this gets done automatically. But when things fail, you don't know why the things are failing. So this is what is going on in the background when synthesis is running. So it creates an intermediate representation, and that intermediate representation is then converted. The intermediate representation is then converted into subsequent representations, which are used for the gate level mapping. Malikarjun is asking, how do we generate clock waveforms for the test bench? Which test bench, which clock waveforms, Malikarjun? I am not sure. Okay, moving along. So when the last one, after you make it identify the D-type flip-flops, you should be able to get something which looks like this at your end on the graph-based representation. I've captured all of these things in the PDFs as well. All the previous things, if I go back, all the previous commands which we discussed are also all captured. These will be actually uploaded in the drive. So you can also go back and look at them after today's session and become more acquainted with the Yosys platform and play around to visualize different Verilogs, how different stages of the flow on your own as well, to understand how synthesis actually happens. Tomorrow, we'll actually go and visualize a bigger RISC-V designs using the same technique. Okay, coming back. So we want to take one last example here. Let's see if, let's do an exit. Let's go back here. Let's do clear. Where were we? We were at project examples. Let's see what is an example 5. Okay. In example 5, you have something which we have described a module, and in that module there are different assign statements trying to perform different basically operations with respect to the marks trees. And we want to now visualize how can we make the tool understand this in the Yosys environment. How does it do different synthesis optimizations on such things? Okay, so okay, Richa in the meantime is asking asynchronous clocks, how do we identify them? That's a very good question. We'll look at that again from timing constraints aspects in the next lecture. Okay, so where were we? We are here. We are trying to visualize different aspects of the code. So I will work on example 5 in the similar technique, and we'll go through certain steps, and then I'll wait for 5 minutes for everyone to catch along and visualize the same thing. Okay, so we'll do the same thing. We are going Yosys. We are doing read Verilog example 5. Okay, and now what we want to do is show what did it identify? It identifies UUP. Our current representation is something which looks like your representation will look something like this. So you have multiple inputs. All of these inputs are going through AND gates and muxes to give you an output Y. Okay, so that's where we are. So this is our just the initial Verilog. We have not done anything on it. Okay. Now the question is this our most optimized Verilog? We may not have written the most optimized Verilog. So simple synthesis tools are able to do simple arithmetic optimizations. And some of them are like, some of these optimizations are like mux tree optimizations and so on and so forth. Okay, so let's do opt mux tree. And if you see what it's creating, internal representation of mux trees, evaluating internal representation of mux trees, then it removed a multiplexer port from our design. So let's see, we'll do again show UUT. And if you see here now, it is a more optimized version of our previous design. It has been able to do optimization on the mux tree. I will type one more command and then I'll let you run all this on your own end to try to visualize this. And then we'll do, the next one is opt clean. And this lets us do final optimization on the wires which are not used, which are useless. And then we again do show UUT. So if you realize what the final output looks like is this. So pre-optimization, you saw how big the representation was, but actually if you optimize it, at the end of the day, that is all the functionality you need, which is so simple over here. So all you had, what we had done before was we had written a Verilog code which was completely unoptimized with respect to the utilization. There were unused wires there, there were unused signals there. With respect to input and output, once we do an opt clean and opt mux tree, it was able to reduce them and get rid of them. And at the end of the day, all this matters. So Rajan is asking, does change the Verilog code? Rajan, Verilog code was trying to achieve a function. Your function still remains the same. What opt mux tree did was it got rid of the wires and the mux hierarchy, which was useless. So before, basically, this is the optimization stage. So in the beginning, if you realized in today's lecture, what I was talking about was you have to understand the synthesis optimization techniques. So this opt mux tree and opt clean, that's what it is doing. This is optimizing your mux representation and unused wires representations. It is optimizing them, and you are able to get a cleaner representation. So now if when you do the mapping into a gate level netlist, that's all you have to map this. You have to map this to a gate. That's all. Okay. So that's what this opt function is doing. It is optimizing your code. Yes, Pradyum, you're right. Absolutely. You can, or Samarth is asking if we can automatically optimize the Verilog code. Yes, you can automatically optimize the Verilog code, but within the bounds of the open source tools, you cannot do a lot. Those are internal representations. Don't worry about them. $3, $12, and all that. Those are some process run things. Okay. I would let everyone try this. I will wait for 3-4 minutes. Then there are a couple of other things. Vishnuvardhan, yes. In the meantime, I'll keep taking questions. Is asking why does the Z goes away because it's an unused port. It's not needed. If you have unused wires, they disappear if you do an opt. Coding method changes the resource utilization. Yes. But then we'll come back to your question on generated netlists for sure. Coding method changes the resource. Obviously, if you write a better code, your tool needs to do less. So you'll have lesser resource utilization. Jagdish, we already answered this. These are Yosys commands. So guys, take a minute, try to reach the stage. We'll come back in 2 minutes to further go, there are a couple of stages of synthesis left. We'll come back to them in a bit. Okay, so Rajan has optimized the Verilog code. OptClean optimizes the Verilog code for your synthesis. It optimizes the Verilog code, obviously, for your synthesis base. Because Balaji is asking, where did the buffers go? The buffers went away because you did not need them from synthesis perspective. Synthesis doesn't do the wire load approximations, and it just does, if it's the same signal, it just eliminates any unnecessary gates. Sharmila is asking, can we use these commands and tool for other Verilog designs? As for sure. I meant waveforms for the outputs, different inputs. So Mallikarjun, we are not doing a Verilog simulation. We are doing the implementation flow for it. I think you have a little bit confusion there. Yes. So basically, in open source, you do not have optimization for everything. There are only with respect to muxes, D flip-flops and stuff like that. You have certain optimizations. If you want to do more optimizations, you have to write a better RTL. Your RTL should be optimized. So now if we move along into the leftover part of the synthesis flow, what we want to do is we want to create a represent. Till now, what we have is a representation which the tool understands. And now we want to create, go towards creating a representation which is a Verilog representation which can be read out by other tools as well. So the first thing to do there is tech map. And once we do the tech map, as you see here, the tool creates different representations, intermediate representations, and then it successfully finished the Verilog frontend. So we are converting it into a Verilog file. Okay. Now we can actually go again and do show UUT. And if you see here, it changed certain representations here. We can actually go and write Verilog test1.v. And now if we go here and see, we have a test.1.v. Let's see more test1.v. You'll see that you have intermediate representations which are being written as Verilog file, basically. Now, I'll give you a moment to do this write Verilog thing. Do a tech map and do a write Verilog, and then I'll come back to your question. And then we'll move along with the library mapping part of it. And in the meantime, the Sky 130 library should already be in the drive. Please go ahead and download that. That will be needed for the next step we are going to do now. And if you have not already downloaded it, please download that. Okay, so next is, I hope everyone has the Sky 130 library. So what we'll do is we'll be doing the lib mapping. So in order to do the library mapping, what I'll ask you to do is wait a second. What I'll ask you to do is go here and let's see. So wherever you have put the Sky 130A, for example, I have over here, I would ask you to go to its FDSC one, Sky 130 FDSC HD, go to the lib and copy the path to any one of them. So for example, I'm doing PWD. I will need to specify this path and then this library name. So that's what we are going to do. The other thing is for doing this, we would want to do it in two parts. One is you can do separate lib mapping for flip-flops and then for the complete design. There are two commands. That's why I want to actually read the Verilog 4 again, because that had the flip-flops. And then I want to do opt clean. And so proc, so I forgot proc DFF. proc ARST, and then I'll do again opt clean. Now I have two modules, UUT and my D flip-flop with asynchronous reset. I would like to map them into my lib files. So in order to map them into my lib files, what I'll do is I'll type the command dff lib map liberty, and then I had copied a path. That's my path to my lib file for my technology library. I want to copy the individual library I want to map to. This is the one I will want to map to. So this is, I have copied that, and then I'll paste that over here. So basically I'm saying map all the DFFs to this library. Okay, and so that's what we did. We mapped all our D flip-flops, as you see over here, in both the modules. Obviously in the UUT module, there was no D flip-flop, so nothing got mapped. What I'll do is I'll show you the rising edge one. So actually, I don't know why this rising edge is not showing up. The rest, everything is showing up. We'll come back to this again, I guess. So this was for the D flip-flop mapping. You can map the overall design after this to the individual or the technology file. The process is the same. The mapper is called ABC mapper. We'll do, instead of DFF lib map, we do ABC liberty, and then we go back here, find the path where my library is. My library is over here, and we do this. Then we specify the specific library I want to map everything to. Currently, I want to map it here, and this is done. So everything got mapped. Okay, now clean actually does any optimizations which are needed after that, and then I can do again write verilog post synth .v. Let's do this. Okay. Now, okay, let's go here and let's see what did I write. Project. Let's clear this. So as we can see here, there is a post synthesis Verilog netlist already here. And now if you see here, different modules have been mapped essentially. So that's what our aim was, and we can see that the modules are mapped to the Sky 130 library as we wanted. So this is the general process of synthesis. Now there are certain specific questions which are coming up, which are with respect to which library do we map to. Those are all excellent questions. So let's understand this little bit. Okay, so typically when we do synthesis, what we do is we map it into the worst case library, because in order to optimize for time runtime, we map it into the worst case timing library, and then during the place and route backend flow, we do a mapping into more than one corner, and optimization using more than one corner, and then STA we do at a lot of corners. So your point is correct, that if I go in my libraries over here, let's go back to the libraries. CD. So I did not want to go into too much details because Puneet will be going into this input output files and what different corner libs means anyways. But for now, if I go here, Let's go into lib. There are library files for different corners and processes, right? Typically for synthesis, what you'll do is you'll map it into the what is the at 100 degrees Celsius is what the worst case temperature with the lowest voltage at the slowest corner. So this would be typically the lib file you will map it to. So that is how the synthesis flow is done using Yosys. That was the objective of the last 2 hours, to make you visualize what do we mean by synthesis, what are the different intermediate representations in synthesis, what do we mean when we say the synthesis tool optimizes for different logic structures. So that is the general idea behind synthesis, what we wanted to present. Now, the first thing which we mentioned today was the timing constraints part of it with respect to the IO delay. That is what we are going to be visualizing in the next lecture, and then we'll come back and visualize the synthesis aspects again from RISC-V core perspective in tomorrow's session. So in the meantime, the source files for the RISC-V core I will upload them, so you will have them. Don't worry about it. Apart from that, that is all we need for tomorrow's session. And the other questions which are coming up, Naveen is saying that we map it in diverse. Yes, as I mentioned, Naveen, for the typical corner, we do the performance check. So we do as I mentioned, sign off STA, which Puneet will get into. There we will do on all of that. Chitra, Rajan, all of this is mentioned in the PDF, which will be uploaded today. So don't worry about it. You'll have all the mapping steps with you. Okay, so that brings me close to the end of today's first session. I hope it was an informative one. So I think there is like a 5-10 odd minutes break that has been planned by the Academy, and then there'll be another 2-3 hour session to catch up on the yesterday's session. Ma'am, I think we are good to go. And what I'm going to do, ma'am, is I'll be sending you this PDF, the quiz aspects, and the files needed for the next session today itself. Sorry for the delay from my end. It slipped my mind that this technology file would also be needed. So yeah, so Firoza ma'am, are you there?
Hello.
Yes.
Yes, Aditya sir. Yeah, absolutely. I'm here. So we will have a break, I guess, now.
Yes, ma'am. And then in the meantime, Puneet will set up and he'll proceed in a 5-10 minutes time.
Okay, so we announce a break of 5 minutes. So there will be 5 minutes of break. So we will resume at 11:36. So we request all the participants to please log in to their system. Don't disconnect. We will start the session from 11:36 onwards. Thank you.
Perfect. Perfect. Thank you, ma'am.
Firoza ma'am, in the meantime, can you just give me the share permission?
Yeah, absolutely. I'm doing that. Hello, Puneet sir. We have given you the sharing rights, so we request you to please share your screen and please have a test run before the session.
Okay, I think you can see my screen, right?
Yeah, absolutely. Your screen is perfectly visible.
Great.
Thank you.
Okay, everyone. So I think it's 11:38. Yeah. So all of you guys are back or still? Can you use your Q&A window and just say yes or no? I hope you guys are able to. Yes. Great. Great. So am I audible? Crystal clear? Can you guys see my screen? This is just one PPT version. And just one more. Can you see this WinZip folder also where it is written Sky 130A? So can you someone just type if they can see Sky 130A? Just write Sky 130A. Oh, great. That means you are able to see this thing. So let's start the second session, second part of the current session. So today, um, I'm not going to just give you a lot of theory, or maybe it is a theory. It depends on you, like okay, how you want to take it. So the purpose of the second half of this session is just to give you the idea about different IO files and what are the different IO files, what are the what is the format of those IO files, why there is a need of those files. That's some theoretical portion we are going to discuss. We are going to discuss in terms of different snapshots. That's the purpose of this thing. Second is I'm going to just show you some files which we are going to use in the next 9 days, 8 days, I would say. And uh, I will request all of you just to open those file once before you proceed further. Frankly speaking, most of the people they are working on the flow, they are working on the netlist, so they have a good idea about Verilog netlist because that netlist is a something they have to write. So they know the syntax, the format of the Verilog netlist, the information which is captured within the netlist also. So those information basically is easily, I would say, sorry, those information. But when it comes to other files, so we what we usually do, whenever I'm saying we, I'm if at your place, then what we are going to do. So at that particular time, it's like something just yes. Yeah. So I was saying like sometime we don't know what all those files, what information is present in those files. And from the flow point of view, maybe we know how to run a particular tool, how to do in terms of just uh, within a tool sourcing a particular file. Maybe you know that particular part. But if I will ask you, like, have you ever opened that particular file? So maybe you can say no. So if you want to do any research, if you want to do anything related to the uh, new thing, practical thing, so it is highly recommended like, okay, you should know what is written inside the file. And here we are talking about the open source. Here we are talking about the open source. When I'm saying the open source and the freeware, it is basically open source tool also, open source PDK also. So PDK in the sense physical design kit, where there is a um, files which you are going to use. Like someone was asking in the morning, I was just checking your the Q&A session, and you were saying like, okay, .lib files, which .lib file, from where we are going to download, whether we have to go with the some industry standard or some third party vendor, or are you going to provide those things? So point is like if you know what is written inside a particular file, what information is there, then you can come up with your own file also. So think in this way, there is a tool that is open source. Open source tool in the sense you can make the changes in that particular tool if you want to do in that particular way. That means you can code the backend of that particular tool also. Now we are talking about the open source files also. That means you can change certain things in the files also. So you can write the files. But yes, if that particular file is a IEEE standard, then the format of that particular file is going to be as per the IEEE format. And if it is like your custom tool, the custom file, then it is okay. The way your tool is going to understand whatever the language, whatever the format the tool is going to understand, you can write in that particular way. So my goal from today's session and maybe the tomorrow session, depends like okay how much I can cover today, is just to give you an idea like what is written inside a particular file, what are the different files, what is the format of those files, and what are those files we need it and why we need those particular files. And if you know that particular part, it is just like a RTL2GDS flow which we are talking about. It is very, very easy for all of you. So that's the purpose of the today's session, tomorrow session. Now, any question till now? Or is this part is clear or not? Just use your Q&A window and just write yes or no, or if you have anything. So I'm going to show you some sample files also, and there are certain files which we are going to discuss in detail. So that's a purpose. Clear, everyone? I think make a interactive session. Just type it. I can see how many of you are just typing it. Okay, so there are I think how many people are here today? Let me just check it from the participant point of view. Okay, 351 participants are there. So I think at least I should get a good yes or no. Great. Very good. So now let's start. Let's start. So this is just a from the slide point of view, I just captured a couple of things. So it is a summary of certain input output files, and I just tried to highlight what information is present in those files. Let's start with these 6 boxes. The first one is the logical library. So think in this way. So when we are talking about a design, so in that particular design, they always remember there are a couple of information we are talking about. So one is the design related information. Design related information in the sense, let us suppose if you're saying I have a very small design adder. So that particular adder is basically is a design. So there should be certain design specific information where the design related things are written. That is the one thing. Second thing is from the functionality, what exactly you are thinking like, okay, adder should do. So adder is just a name, but yes, the moment I mentioned the adder, I'm sure like, okay, everyone everyone understood like, okay, this circuit is going to do the addition. But what type of additions? It's like 2-bit, 1-bit, 2-bit, 4-bit, 32-bit, 62-bit. That's a thing I'm just talking about, functionality. Another thing is the way you design the adder, the circuit of that particular adder. So are you just doing the 32 parallel adder, or maybe you have used something which is like in a look ahead, carry look ahead adder? These are the things. Basically, these this is something which is literally the functionality. Like, so there should be a file where we are going to discuss about the logic. We are going to talk about the functionality. They're going to be the third thing which you need to understand in terms of how fast this is going to give you the result. Now, maybe it will take 1 day, 2 day, or maybe you just need it within a 1 clock cycle, 2 clock cycle. So that means certain timing related information supposed to be there. So in some file, some timing related information is going to be there. So think in that particular way, like, okay, these are the three things. Now we are creating a chip. That means in a chip, right now whatever I'm just talking about, that is I'm just talking verbally, but in the chip it is going to be the physically, like in a physically, in the sense, in the chip some transistor is going to be placed. Now the transistor is going to be placed, you cannot so you have to tell the tool, or you should know, or the foundry, like, okay, this transistor is going to be placed at the upper corner, upper right hand corner. And just if you cannot tell me like, okay, you can just place anywhere, because that is your chip. So you have to tell me like, okay, if I'm going to place this thing at this particular place, then the results are going to be good. That means now we are talking about the physical thing, like, okay, where exactly these transistors supposed to be placed. And now physical thing, that means we are going to talk about certain coordinates. So that's basically the physical library now I'm talking about. That means physical related information will be there. Now this is something which is coming from our end, but we want to fabricate it. So if you want to fabricate it, then someone was asking the I think last yesterday they were asking about which technology node. Now what is the meaning of the technology node? That means now we are talking about something with respect to the foundry, like, okay, on the what is the size of the transistor, and accordingly from the foundry point of view, what are the rules we are talking about. So that comes under the category of the technology related information. So that technology related information, any foundry is going to provide you that. But yes, the provide you in the sense, in what way? Is it going to provide you in the form of PDF or the Word doc, or just a voice message or the video message? If all these things are there, then you have to see whether your tool can understand that voice messages or the images, whether tool can understand or not. But right now our tool are not that smart, like you can just say like, okay, there is a transistor placed at this particular corner, and it can understand automatically. So for the tool point of view, basically you should have a file which is a technology specific file. So this is a combination. These are the different information I'm talking about. And there is a one more factor of these things in the design, that is related to the area. Sorry, area comes under the physical power basically. So power related input output files I'm not talking here, but yeah, that is also a one of the area where you have to provide certain information to the tool, like, okay, if you want a power related analysis, then tool should know the power related thing. Okay, someone was asking like, okay, any IO files are needed because no such files are uploaded on the drives. Okay, so Naveen, uh, related to the files, there are two things. One, if I will just check with Aditya once again. I think he have shared with you one slide where you have to download from a GitHub, and from that particular GitHub, that has all the files. Everything is going to be there. All the tools are there. It is going to give you uh, all the files related thing also there. So I think you may have set up your environment, but maybe you just missed just to explore that particular part. One version I will just show you. So maybe after today's session, you just go back and just check it. That's the one thing. Another is, if it is not present in the same fashion, then maybe we will upload that particular part in the drive. Then you can just check that. You can just download from there also. So I will just check once again with Aditya whether you have all those information or not. But I think you should have, if you have downloaded from the GitHub. Someone asked like, okay, the 6 box says it includes all the stages of the IO files, or else the particular stage IC design, please correct. Okay, so so I think by now you're clear. This is These 6 boxes are not the stages of our RTL2GDS flow. These 6 boxes are related to the category, the way I divided. the way usually we divide the different files in a different category on the basis of their information. Now I was just talking about the logical library. So logical library, it has a timing information of standard cell, some soft macros, hard macros. It has information about the functionality, some design rule information like max trans, max cap, some power related information. So these informations, you can see it is all about the technology related thing. So I will just show you some sample files about the logical libraries also. Now, if we are talking about the physical library, so like I have mentioned, it is going to give you the physical related information, the coordinates. Now, whether it is a transistor or the minimum weight or the pin location and the wire, the routing when we are going to do the routing, all those things, it is going to give you related to that particular part. Then technology related, like I have mentioned, it is usually this file is coming from the foundry. I would not say the file is coming from the foundry. It is basically the information which these files have that is coming from the foundry. Now, depending upon the tool provider, whether it is a Cadence Synopsys Mentor or maybe some open source, maybe you can design your technology file yourself. So if it is your tool, you know, like, okay, how your tool is going to understand a particular minimum width or the minimum spacing. So your syntax can be different. So but yes, the information is going to be coming from foundry, and then it is usually come from the tool. So when we are working with the technology file and when we are working on the open source and when we want it to if we want to design something, the first thing we have to understand whether our tool is compatible with those technology file or not. So it should not be like, okay, if you are going to use a open source tool and the syntax which you are using, that is the files which you are using, that is compatible with the maybe some Cadence or the Synopsys tool, and your tool is not compatible with that. When I'm saying the compatible with that, that means maybe your tool is not able to read those particular files. Read in the sense your tool is not able to understand what information is present in that particular file. So always remember, whenever there is a file, when I'm saying the file, it is a text format file. It is a English, it's written in the English language, and you have to understand like, okay, whether those syntax, those format tool can understand or not. Then there is a something which is a TLU plus file. So basically this TLU plus, I just took a example. So in our case, when I'm saying our case, in open source, TLU plus files are not required, but in an industry, TLU plus files are required. So I just took that particular example, one of the synopsis example, like, okay, this is the TLU plus file. In our case, it is a very small syntax, very small file, but I just want to highlight like, okay, there is something known as a TLU plus files. I will just show you one sample of that TLU plus file. So for this particular course, as such, you don't need to understand, but I just want to cover that particular portion. So it's a technology file. So TLU plus file is basically again a technology file. So it's a specific name of that technology file. Then netlist. It is very long netlist we are talking about, and this is the design related information, like I said. And then SDC is the timing related information, is a constraint file. So this is a industry standard constraint file, and if you are going to ask like what is the full form, it is basically the Synopsys design constraint. So this is the basically what happened, that they came up and they initially the file was in that particular way, and then later on that become an industry standard. But name we are using as a SDC file. Still we are using the name in that particular fashion only. Okay, so someone was asking like, okay, it's a similar to the QRC tech file. Yes, good, Naveen. So that is the QRC tech file is related to the cadence, and this is related to the synopsis. Now let's go one by one, all these 6 boxes, and then I will show you there some samples of file in our environment which we are going to use at the Sky 130 we are going to use. So I'm going to just show you that particular file, some directory structure, some file structure I'm going to use. And the purpose of that is so that you can go and you can just check like, okay, what is written there. And one of the sometime I'm going to ask you like, okay, what is written in this particular file. At that time, we should not be just like blank. Okay, we don't know about this particular file. So logical library. So in the logical library now, see if any particular formula is written. So whenever we are going to do a particular calculation, so in that particular calculation, if you remember in our school days when we used to do our calculation, so sometime our professor they just detect them, they just give us the zero. Why? Because what happened? We mentioned r equals to 5 and they will say like, okay, it's a zero because it can be a 5 milli ohm also, it can be a 5 ohm also, it can be 5 kilo ohm also. So this kilo ohm, milli ohm, or maybe it's a 5 ampere also, maybe we don't know. So the point is they always ask, they always mention, and they always try to give us the clarity of the importance of the unit. Like, okay, if you know the unit is important. Now, why unit is important? Because for you, you are doing a calculation. For you, maybe you are thinking like, okay, it's very obvious, like resistance going to be in the ohm. Yes, it's very obvious, but how it is obvious, like it is going to be the kilo ohm or it is a milli ohm. So in the same fashion, try to understand from the tool point of view. So tool is basically a program, and in that particular program you're going to read certain information. So there is a file, in that particular file it is written r equals to 5. Now how the tool will come to know like, okay, what is this? So maybe you can hardcore, you can say like, okay, wherever there is written r, so the programmer is going to write in this way, it is in a ohm. That means resistance, and this is a ohm. Okay, good. So that is something is a part of our default value. So programmer usually do in that particular way. Like, okay, if nothing is specified, consider that as a ohm. But if you want to specify, if you want to say like, okay, I don't want to mention into ohm, I want to mention it a milli ohm. So there should be a way you can change the unit of the resistance. So it is very important, and the reason I'm discussing this part, because when we are doing the analysis, when we are going to use the tool, I have seen many times like there are two different tools and their default values are different. When a particular tool is designed by a single person, so if there are two tools designed by a single person, so then you can assume like, okay, both the tools have a default value resistance, the unit of the resistance is a ohm. But if both the tools are designed by someone else, so both two individuals, then if you are going to assume it like, okay, both are going to use the default value of the resistance as a ohm, a default unit, maybe one can say like, okay, nowadays our designs are so complex, we are not going to use any resistor with the ohm, is going to be a milliohm, or maybe it is going to be in these type of design we are going to use the resistor of a high value, that means it's in a kilo ohm. So there are chances, and usually it happen. So whenever if particular information across the tool, if you are shifting from one tool to another tool, I have seen a lot of time like the units are different. So as a debugger, as a debugging, if you are going to do the analysis and if you want to do certain check like, okay, whether your results are as per your expectation or not, you should know which tool has a default value, what is the values written in a particular file, and then you can do the hand calculation and figure out like, okay, whether it is in the same fashion or not. So when I'm going to just give you an idea about the timing analysis, I will show you like, okay, how things are going to change if you just assume a couple of things. So in a logical, that is one of the parameter like we are going to define. Sorry, guys. So yeah, so I was saying like, okay, in logical libraries, we are going to define in terms of all the units. Then there are certain default parameters like these are the maximum transition input pins. So we will discuss a little bit about all these parameters. Then the PVD conditions. So PVD conditions is a process voltage temperature. So that means a particular file is characterized. So characterized in the sense in our books there are certain formula, and on the basis of that particular formula we do the calculation and we come up with a certain numbers. So like I was saying, like, okay, if I'm doing certain calculation, if I'm saying like, okay, this is the delay of a particular cell is a 2 second, 2 millisecond or 2 nanosecond. Now then definitely you're going to ask like, okay, Puneet, this 2 millisecond is in all the conditions. Now, what all those conditions in the sense, is it if I'm going to operate this particular cell at a minus 40 degrees Celsius or at a 0 degree Celsius or at 25 degrees Celsius, and what about the 75 degrees Celsius? In all the cases, do you think the delay of this particular cell is going to be the 2 millisecond? Maybe I would say yes. If I will say yes, then maybe you can come and you can ask me like, okay, how? It's not possible because the mobility of our electrons or the holes that's going to change is going to change with respect to the temperature. So I think you can understand from the semiconductor point of view, temperature, on the basis of temperature, a lot of things are going to change. So if a lot of things are going to change, and if I'm just giving a value of a 2 millisecond or 2 nanosecond, that means I should be able to give an idea like, okay, this is the temperature. On this particular temperature, this is the value. If the temperature is going to change, the temperature is going to your value is going to be different. Similarly, when it comes to the voltage, so I'm sure we have discussed, maybe you have heard this particular part, like, okay, the voltage, what is a voltage? These libraries or these particular cell, what is a VDD basically, if I will talk about. So you can see like, okay, in a 180 nanometer libraries or maybe in a 7 nanometer libraries, if you're thinking like, okay, we can use the same VDD, that's not the right thing. So if you remember in some books, not the remember, if you will just go back, if you will just see some books, they are still using a VDD of a 5 volt, or in a advanced book, not the advanced in the sense, the modern, the updated book, and the book, if someone just written the nowadays, maybe they are going to use it as a 1 volt or the 2 volt. They are going to use these numbers. So if this is about 5 volt, 1 volt, so that means that is not a generic thing. It is going to be changed on the basis of the technology, on the basis of the design. So if I am going to give you like, okay, this is the delay, and this is the way the current value is there, then definitely you're going to ask me, okay, what is the voltage? Similarly, then the process. So the process is basically, it is coming from the foundry point of view. Like, okay, which process we are talking about. So we are not going to discuss too much in detail about the process point, but just to give you an idea, we have NMOS, PMOS, and the NMOS and the PMOS, in a particular, like yesterday, we did this some simulation and some output was there. In that particular output, there was a inverter, in a PMOS was there, NMOS was there, and that particular PMOS, NMOS, you can say like, okay, on the basis of the fabrication, that means on the basis of the process which they have followed, on the basis of that, both the transistor were fast. So both the transistor were typical. Let's say the typical in the sense, the some certain value you have provided and you're saying like, okay, this should be the dimension. But somehow during the fabrication, the dimensions has changed. Now because of changing those dimensions, when I'm saying the dimensions, it's like the width of PMOS. Let's take an example, width of the PMOS. That width of the PMOS, that change. Now the width has changed, then definitely your performance of that particular PMOS, that's going to be changed. So either it's going to be slow or it's going to be the fast with respect to your typical number. So typical in the sense on the pen and paper, you say like, okay, this is my typical number. So the process is basically we define in that particular way. And when I was talking about certain current, I was talking about certain delay, then definitely this process, whether it is a fast, it is a slow, or whether PMOS, NMOS both are fast, both are slow, both are in the typical or whatever the combination. So that's going to affect our final values. So that means you should have certain information while I'm doing those characterization, those numbers. If I'm sharing with you, then at least I should be able to give you those ideas. So this parameters, basically, I will tell you like, okay, this is the thing. Then there are a lot of other information we will see as a part of a snapshot, or you can just open those files and you can understand those things. So logical library, we will discuss in detail also the .lib files, and .lib files, it has all these informations, the timing, power, informations are there. So just to give you a snapshot, if you will see this particular file. So this is some library. This is some library with a 180 nanometer, and that 180 nanometer, it is if you will see, it has a time unit, voltage unit, current unit, resistor unit, like I was talking about. Then in the timing information, if you remember, there is a something as a transition time, there is a something like in a propagation delay. And when we usually calculate the propagation delay, we usually talk about 50% to the 50%, or in the transition time we usually talk about the rise time or the fall time is like time taken by a signal to rise from 10% to 90%, 90% to 10%, or maybe 80 to 20, 20 to 80. So all these numbers, basically this is as part of our definition, but how we are going to capture into the file, there should be a proper syntax. So in the timing information, you will see all these things. So we are going to discuss this specifically this particular file in detail, because when it comes to the timing analysis, when it comes to our RTL2GDS, one of the important thing which we are making sure nowadays, that is a timing, like okay, the timing information should be there. So these are a couple of snapshots. So this is initial was just generic information, then these are related to the power, and there are certain things with respect to the cells, like okay, in a cells, what are the different capacitance are there, rise capacitance, fall capacitance. So these things are there. Now we will discuss, don't worry. So about that particular file, I will open that particular file, I will discuss in detail each and every component about these things. At least this is a file which you should know by heart. So I'm going to discuss those things in detail. But just to give you an idea, like okay, in a library, now if you will see here how we what we have done basically here. So if you are going to characterize, if you are going to characterize a particular data, a particular cell, and you are saying is as a let us suppose the inverter, if you are characterizing that particular inverter, and that if you are going to characterize in what process. So if you will see, I just took an example of a IO spatial cells. So if you want to see, there are the process fast, 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 fast. This is a process. That this is basically the core supply. So this is one with respect to the core supply. This is IO supply, and this is a temperature. So if you will see, the once I'm going to characterize, that means whatever you have done it yesterday is a simulation. What the simulation you have done. So I'm just talking in that particular way also. Let us suppose you simulated it and you want to capture the output of that simulation in a particular file in a with different input conditions. Now in that particular different condition, on the basis of the PVT corners, process voltage temperature. So this is what I have just mentioned. Like okay, here different nomenclature, how you are going to write the nomenclature of your file. So what is the temperature, what is the voltage, what is the process, and then you will just write it. So once you will see the library in your once you're going to download it, then you will see different there are a lot of libraries, and you have to understand first, like, okay, what is the what is the nomenclature, what is the meaning of those library. It is not like you can just save it as a Abhishek dot lib, or Puneet dot lib, Aditya dot lib, Firoza dot lib, or the ma'am dot lib, the first dot lib. You can do it. That's not a problem, but that's going to create a problem to you. You cannot understand, like, okay, whether this particular library is characterized with what corners, what information. So what you're going to do, every time you have to open the file and you have to just check it, like, okay, inside that particular file, what is written, what is the temperature, process, voltage is written inside that particular file. So in place of that, in an industry, what we are doing, we are the nomenclature of that particular file, we are just making in a particular fashion. So this is just for that particular example, just to give you an idea, like, okay, the way the nomenclature of a library usually people decide. Someone was asking, like, okay, what is the IO supply, power supply? So basically, Vinendra, if I am not wrong, yeah, Vinendra. So if you will just see in the IO, I think when in a IO cells, so I think um I don't know, like, okay, how much you know about the IO cells. So but here you can see from the IO cells, so we are talking about when IO power supply, that means VDD I'm talking about for those particular IO cells, and then the core power. So so IO cell is basically at the boundary of a particular core. So in that particular, what is the core su supply and what is the IO supply? It can be different, it can be same. So right now here you can see it's a different, and on the basis of that doing the characterization. So usually IOSAs, they have two VDD, one for external, one for internal. So all those things are there. So if two different things are there, then in that particular case it is like that. Okay, so now let's me show you before I just go here. Maybe I will just show you one file. So let me just come here. So what I did, I just downloaded a one Sky 130 a little bit, not the complete PDK, but some portion of that particular PDK I downloaded it, and I'm just going to just show you that particular part. But before that, in a logical libraries, whatever we have discussed, so still there are a lot of things which we have to discuss, but whatever we have discussed till now, anyone have any question? It's just like I'm just speaking from the last almost like more than half an hour. So anyone of you have any question? So if you don't have any question, just say no. And if you have any question, just type that question. Just take 30 seconds and then. Can you explain FFSS process? So Rajesh, I gave an idea. What is a fast, fast, slow, slow? So fast, fast in the sense both transistor, NMOS, PMOS, both are fast, both are slow. Okay, so that's the process I'm talking about. So if you remember, I mentioned typical numbers, and then while you were doing the fabrication, the number, the size of the transistor that changed, and when it changed, it can perform fast also, it can perform slow also. So that fast, fast, slow, slow is on the basis of that. Aparna, fast in the sense timing point of view, in the sense, okay, it is it is giving you the result faster than the typical number. So when let us suppose you're saying 2 nanometer, so 2 micrometer or 2 nanometer, your the size of your transistor, and now let us suppose it decreases. it become like plus minus 10% variations is there. Now, if that variation is there, then after that, the new size, whether your transistor is performing fast or your transistor is performing slow, that's a something is related to the fast and the slow thing. Okay, someone was asking what if we want to add the temperature value to the .lib file. So yes, you can add the temperature value, but the thing in this way, if you have characterized your library with a particular temperature, then it is not usually recommend like, okay, you just manually just change the temperature or the voltage, because if you are going to do manually change the value of the temperature, then the numbers can be different. So usually you have to, that's the reason if you will see there are a lot of libraries they have with the different temperature values, and you have to use that particular temperature value while you are going to do the analysis. Okay. Then someone was asking about one second. Thing. Okay, someone's Malikarjun, apart from these, there is also HV processor. Yeah, so that HV uh, basically that is a maybe you are referring to HVT LVT process. So that is related to the threshold value. So the CMOS, the MOS which we are talking about, what is the threshold value? It is a high threshold value, low threshold value. So that's come under the category of the HVT LVT. HVT high threshold value, LVT is the low threshold value. So think in this way. See, whatever we study in our college, in our books, like okay, there is a threshold variation, there is a threshold value. Now from the fabrication point of view, what if you're going to change something there, and then you will say like, okay, this is my new transistor. Now how the foundry is going to tell you like, okay, this is your new transistor with a high threshold value. So you, that cell is going to be different, it will have a high threshold value, and then you have to do the simulation. So whatever the simulation you're going to do, as such, it is an inverter, same technology node, it is an inverter, but now it has a high threshold value. So then we will just from the nomenclature point of view, we will just say like, okay, this is a high threshold value inverter. So that's the way we usually define it. Okay, then if fast slave value is 0 and if I change trend, it will work. No, it will not work. So it's just like you are manipulating, you're changing the inside value. So okay, so how should I explain you? Okay, so think in this way. Maybe who just asked Naveen? Naveen, maybe you are at the age of 25 right now. Okay, so as practically, I would say like maybe you just uh, as per the time when you born, you came in this world. As per that, it is a 25 year. You're 25-year old. But what you have done in your 10th mark sheet or maybe in your Aadhaar card, you just change the value, and you change the value and just put it like as per that your birth. Now, as per that, you become a 20-year. So as per the Aadhaar card, now you're a 20-year-old, but actually you're a 25-year-old. So biologically, basically you're 25-year-old, but on paper it is a 20-year-old. So what do you think? It's going to work? Yes, it's going to work, because everywhere on the paper, bank, education, we are going to evaluate you on the basis of 20 year. But actually the value, the output which you are going to give us, that is as per the 25 year. So that means you are just uh, the way you just change your values. Similarly in the files also, if delay value, when you have did the characterization at that particular time, the delay value was coming 10 nanosecond, and that is with respect to a certain process, fast. Then manually, if you will just make it slow. So for the tool, it is a slow 10 nanosecond. So it is not going to give you the it is going to solve each and everything accordingly. But after the fabrication, when you will get your chip, and in that particular chip, when in the real world it is going to work, it is going to work as the fast because that's the actual thing. So that means your chip is not going to work. So that was my point when I was saying like, okay, it will work or not. Tool point of view, it will work, but in a real world, it is not going to work, because it that at that particular time, it is going to work on a basis of the actual thing, which was the fast. Okay, so Animesh was asking at any of the development stage, should we write logical libraries or other libraries? So, Animesh, as such, you are not supposed to write logical libraries yourself. Nowadays, tools are smart enough. They are going to write it because that's the easiest way. With the help of a tool, with the help of a program, you can write it. But if you want to write, if it is a very small thing, and if you want to write, you can do that particular part. So for the from the research point of view, from any new innovation, I would say from that angle, if you want to write, you can do it. And that's my motive, to give you an idea, just to explain you the different files and the syntax, and that at least you should have a clarity, like, okay, what is information is present, if I will change, what is going to be happen, whether I can change it or not. Okay, then the next one, how the process corner is related to the fabrication of the chip. I think this is a big topic of discussion. So some part of this I'm going to discuss, I think in the second last day, when we are going to discuss certain DRC, LVS related thing. So just let's discuss this thing some other time. Doping variation, yes, you got the right thing, Panditi Lakshmi, if I pronounce your name correctly. Okay, then we were talking about some more worse condition for the hold is 125 minus 40. Okay, so this is too technical for other people to understand from the hold analysis point of view, but yes, you are right. If we don't have any SSS library, then how will it affect our design? So, Venkata, Reddy, basically you are asking like, if you don't have any fast, slow, typical library, how it will affect our design. So you will have. So you can say I have only typical library. I don't have fast or the slow libraries. That's okay. But at least whatever the library you will have, it is going to be characterized with a certain process. That process can be typical process, maybe. So if you have, you can say out of three, if I have only one corner. So this is basically the part of a corner. If I have only one type of a library, how it is going to affect my design? If that's your question, so it's just like if I will ask you like, okay, if you are in a Bangalore, and if you have to travel from your home to your office, or from your home to your college, and if I will say like, okay, it will take half an hour. So that's a way. Now in the real world, I miss, like, okay, if you're going to travel at a peak time, like 9 o'clock, 9 a.m., then it's going to take 1 hour. If it is in the midnight, it's going to take half an hour. If you're going to travel in a 4 or 5 p.m., then it is going to be take 45 minutes. So the point is, I'm not giving you the complete information. Now, in the real world, when your chip is going to be there, maybe in certain condition, it will work. In certain condition, it will not work, because when you did this analysis, when you did the testing just to make sure like, okay, whether your chip is working correctly or not, you just did it for with respect to the one library, which is maybe the typical library. Now, same thing, like I said, half an hour. That means your analysis, and if you have to reach your college, and your there is some lecture at 9:30, maybe you will say like, okay, let's take a buffer of 15 minutes, let's start at 8:45. But actually, if you will on the road, then you will come to know it is going to take more than 1 hour to reach your office or your college. So why? Because when I gave you the data, I just gave you the data, the midnight data. Like in the midnight, you can reach in a half an hour. So that's that. In that particular way, if you will have less data, then there are chances like your design is not going to work. Okay, I think rest of the thing is same front and back end. So it's all about front and back end everywhere we are going to use it. Particular temperature, then need to write the parameter in a specific library, then I can use it. Okay, good. Okay, what else is okay, great. I think good questions. First of all, I love like okay the way you guys are asking questions. Now, if I have a PDK library which is no having any corner specific, how can I do the worst case analysis in that case? So I think Shilpi, we are going to discuss that thing. I already answered you. So if you have one library, you can just do the analysis on the basis of that. So the worst, the best, or the typical, it is basically the subject. It's with reference to something. So if you have one library, it depends on you whether you want to do the analysis with respect to that library. Now, if you have two libraries, then definitely you have to mention one is the worst, one is the best. You have to do in that particular way. So it depends like, okay, how many files, how many libraries you have, and how accurate you're going to do the analysis. So in industry, people do the analysis on the 100, 200, 500 different conditions. And that's the reason they were talking about the design corners. Now, in a general, just to understand whether my circuit is going to work or not, we usually do the analysis on the one corner. It's a typical corner. So just to make sure my design is working, I'm getting an output, my tool is working, my flow is set up, complete, everything is there, then so one set of library is more than sufficient. It's just like if you are going to fabricate it, and if you are thinking like okay this particular final product supposed to be into the market and people are going to use in each and every condition, in that particular case you should have couple of libraries, 2, 3, 4, 5, 6 libraries supposed to be there. So that's that depends like okay what is your final goal, whether your final goal uh, is basically to capture to make a product out of that, or it's just like to do the analysis just to understand the behavior of the circuit. Okay, so now come back. I think I answered most of the questions. So let's see this Sky 130. Now I'm going to just show you couple of things. Be attentive the way you are doing till now. So here you can see there are the tech libraries. There are a lot of other libraries also. Okay, so people are also asking about the corner analysis using open source EDA tool. Hmm. So we will talk about this Zakir Hussain, like okay, what is the corner analysis and how we can do it. Let's talk right now here. Then maybe you will get the answer of your question. So here you can see in this particular I would say tar file or the zip file, I just downloaded couple of things. So here you can see by name, it is a lib.tech, libs.reference, and there are certain config files basically. So now when I'm saying the config file, let's start with here. So it will have certain config file with respect to your setup. So this is right now it is just empty. So um, I haven't downloaded a lot of things here. Now let's talk about the reference file and the tech file. So let's talk about the reference. So now in this particular reference file, you can see this nomenclature. This nomenclature is very important for you to understand. So here you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different type of folders are there. So in those 10 20 10 different folders, right now it looks like the folders. In those folders, if you will see from the nomenclature point of view, it is Sky 130. It's showing the technology and the PDK type. Then we are talking about certain FD, and then there is a SC, some process related thing. Then we have MS, LS, LP. So all these things are there. Now, what is this? What is inside this? And this is basically type of libraries we are talking about, like IO. So it's very easy for you to understand, like, okay, here we are talking about the IOs. So IO library will be there. So these libraries, once you will go inside that particular directory, then you will see there are Verilog files, there are spice files, there are some magic left, then there are the dot lib, there is the lef left. I'm going to discuss what is the lef related thing. Then they have the different type of syntax or different type of files are there. And what I will suggest you, just go at least once in this particular workshop. Just go and just check it. What is inside this? So there is something written as serial. Just double click. Let's see what is there. Now here you can see everything is written in the English language. What is there which you cannot understand here? You can easily understand, like, okay, this is something written in the English. And now you can also understand what is written here. So here it is written PowerPad library. Okay, this is a PowerPad related libraries is there. It includes the corners and the fill cell sub circuits. That means it has a information related to the fill cells. And then just see, this is a syntax. What is that syntax? Sub-circuit is there, some name is there, and then we are talking about some plus, and then we have certain syntax. That's all. And then here it is a VSS A, VDD A, then some switches is there. And obviously, if you have some idea about the schematic, then you can easily understand, like, okay, VSSA, something related to the VSS. VDDA, that means something related to the VDD. So here we are talking about the different pins, like, okay, these are the different pins. Now here we are talking about VSSD. Here we are talking about, so these are basically what? These are basically the different voltages, domain, you can say, or voltage pin, you can say. Those nomenclatures are there. And then they have different definitions. So what you have to understand, you're not supposed to understand each and every top to bottom everything about this particular file. You don't need that particular thing to understand. It's just a matter, like, you need to understand one syntax and that is done. Then everything it is repeated here. So this is a sub circuit, the definition of that particular cell, and then this is the end. So only two lines you have to understand. And if you want to understand, you can just go on a Google and just check it, like, okay, what is the meaning of this thing. I'm 100% sure most of you already knew this particular part, what is how we write these sub circuit related thing. Similarly, if I will just go back, oh sorry, now let's this is just a doc which is empty right now. Let's talk about the dot lib. Okay, so I think this is the dot lib is empty. Wait a minute, let me just see. Yeah, so now I just pull another one. In that you can see different dot libs are there. So I just which one is this? This is a SCHD. Inside this, if you will see, this is a dot lib file. Now here in a dot lib, what I'm going to do, I will just open one dot lib and I will just show you, like, okay, what is whatever we have discussed till now in a dot lib file, whether that is mentioned there or not. But before that, if you will see here, this is the nomenclature we were talking about. This is some SCHD library. Now here you can see TT is a typical, SS slow, FF fast. So you can see the way it is divided. So first category is with respect to the process. Second, you can see within the TT or within the SS, they have a different temperature. So in a SS, you can see they have a temperature N. N means negative. That means minus. Some places people are using M, some places people are using N. So it's just a way people usually write it. So N is negative 40, negative 40 degree. So these are all negative 40, and then the slow they have this 100 degrees Celsius. Fast was also negative 40 and 100 degrees Celsius. In a typical, we were not doing the analysis. So here there is no analysis with respect to the N40. They have the analysis with respect to 100 degrees Celsius and 25 degrees Celsius. That's all. Now you can ask me, like, okay, in the case of a typical, why we don't have N40? So there is a complete different team, mostly what happened, the way the team, there is a different team, they may have done the analysis also, and they did the analysis with respect to the typical N40, and then they figure out like, okay, so let me, if I will just draw one diagram here so that you can easily understand. So let us suppose if I'm saying this is my a box. In this particular box, these are the four corners. That means if I can verify my design on these four corners, that means I'm just covering each and every scenario which is inside this particular box. And that's the reason we were using a terminology of the corner. That means we are doing the analysis on the corners. And if on those corners things are okay, that means anything between these between this box, any combination which is lying here anywhere, that means that is good, that is good to go. That means in the real world, if I can make sure that my chip are working on these four corner, all these corners are, all these cases, all these combinations are automatically covered. And that's the reason here in this particular case we figure out like, okay, that is not required. So maybe after the analysis they figure out like, okay, that is not required basically. So here if I will come back, so that's one of the reason we don't have all the corners. But yes, you can, there may be some team, not the maybe, there is some team who did this analysis and they came up with this conclusion like, okay, these are the corners and all the other combinations are inside these particular corner. So as a engineer, if you're going to ask me like, okay, if it is a new design and you are going to use a new library, so how can you make sure like, okay, in my design everything is going to be covered in those corners? You're right, you cannot figure out until unless you're going to do the simulation, and you will just see like, okay, whether those are the things. So in an industry, what usually happens, there is a team who's going to just work on, they're going to run hundreds and the 200s of corner, and for the designer they come up with the 10 or 20 corners, that's all. So that's, so basically the industry is happening, industry is working on that particular case. Now the that particular team, when they are running 200 corners, obviously they are not going to run on the actual design, they are just going to run on the sample of the design, the similar thing, and then they are going to make sure like, okay, the design is similar to that small test case. So that's the way industry is working right now. Okay, so now let's see what is inside these particular files. So let me open a particular .lib and I will just show you what is inside that particular file. Yes. So I think you guys can see in my .lib file. It's just open in a notepad plus plus. Am I right? Yes or no? Can anyone just say yes or no? Okay, great. So whatever I have discussed is in the same fashion, but only obviously it is a more advanced library. It will have more advanced information. It is a .lib, and few of the things we are going to discuss today, few of the things we are going to discuss tomorrow, because it is very important for all of you guys to understand what is written inside our .lib file. So this is the library. This is just a syntax. Again, this is the IEEE standard, and then this is the name of the library. You can here you can change it. That's okay. You can say okay, it is a Abhishek library, it's a Puneet library. But obviously, if you're going to change it, your tool is going to understand this particular library with this particular name. Then there are certain things they have defined as a like we define the functions. They define like okay, the clock weight library string. Okay, so I think right now no need to understand this particular part, but yes, this is something is there. What we have discussed, we discuss in terms of what type of delay models. Delay models are basically the lookup models. Now, what is the lookup models? Lookup models is like you will have certain table. On the basis of that you will say like okay, this is the delay related thing. I will show you that particular part. Now you can see the small things also they have mentioned, like okay, in the bus naming style, what exactly you are going to use, what is the time unit, what is the voltage unit, leakage unit, current unit. Now in terms of the resistance, in terms of the capacitance, everything is they have captured here. So this is basically the I would say the header of this particular file. Now, if you will see, then they have certain default value also. So if you're talking about the leakage power, so what is the default value? Everywhere it is written like in a zero. So if you are talking about the fan out, so somewhere if you forget, you in the sense if the tool need a fan out of a particular cell, fan out load. Now in that particular case, if that is not written with respect to a particular cell, then the tool is going to pick this default value. Input pin cap, output pin cap, then the max transition, what is the default value? So all these default values are written here. So this is like the tool understood from tool in the sense if any program need a particular default value, it is going to take all these default value. Then we are talking about the operating conditions. So this is basically the operating conditions like, okay, 1.44, the process one, temperature is -40. We are talking in that particular way. Now you can now you can see here it is written -40, and if you will see the name there also it is a -40 will be there. 1.44 that voltage is there. Now this is a slow process. That slow process portion is written here. Okay, so someone was asking like, okay, what is the meaning of a tree type, and uh, what is the meaning of this balanced tree, unbalanced tree, or what does that mean? So, Naveen, for this particular part is mainly related to the algorithm. It's basically the type of model we are talking about. So when we did the calculation, in few cases it depends like okay whether we are talking about the balance tree, we are talking about there are three types: balanced, unbalanced, or there is a one more which I just missed that particular name. So it is basically what type of structures there. Maybe in the next session I will just try if I can just show you that particular part, like okay, the way it is designed. Now, a little bit on the lower side. Now, this is something which is a lookup table I was just talking about. So here, this is the power related lookup table. So now they are talking about this lookup table. So lookup tables is just like in a matrix. So consider this like in a matrix, the same thing is happening. In a matrix, you have two x's. And then there is a certain values are there. Now, if you have two matrix, let us suppose you have the 2 cross 1 matrix. So in that 2 cross 1, which one is what is that particular 2 cross 1? How you're going to define which is a matrix? What is a variable basically? So here you can see this is a power input 1. Here again they are using the power input 1. But if there is only one variable, then it is an input transition they are talking about. If there are two variables, then the second variable is going to be output net capacitance. So this is the power related. Similarly, if we will talk about certain lookup tables with respect to your delay related thing, then again we will have certain delay related lookup tables. So all these are basically, you can consider these are the templates so that tool can understand like okay, what is the name of the lookup table I am supposed to refer, and in that particular, what is the meaning of the variable 1, what is the meaning of the variable 2. So all these things we have captured as a part of a header of our .lib file. Then let's move little bit on a like lower side. Then this is again one of the things which I showed you, like okay, what is in terms of the threshold values. So transition time, propagation delay in that particular case, what is there, like okay, it's 10 50 to 50, or basically 20 to 80, 80 to 20. All these informations are here. Like okay, when you have characterized, what basically you have considered it, whether you have considered 2020 or 8080. Now, this is the place from where the cell definition started. Now, when I'm talking about the cell definition, like okay, what type of cell you have in that particular cell, what are the different information is present. Let me just maybe what I will do, I will just pick a very easy cell so that I can just give an idea easily. Like okay, these are the cells, and then maybe we can come back and maybe we can just discuss some complex cell, because when I'm saying the cell, AND gate, NAND gate, these are also cells. When I'm talking about these cells, a level shifter is also considered as a cell. So I just want to make sure I should give you the reference of a cell which is very easy for you guys to understand. Let me see if it is a, even if it is a flip-flop or something, that is, I think that is also okay. That is a part of some other library. This is a and 4 cross 1, 4 underscore 1, but that means it is a, it should be AND gate. Wait a minute, let me just check it. It is a AND gate. A, B, C, D, and then it is going to be X. Yes. So this is basically the AND gate, but this is a 4 input AND gate. What about if I can show you and 2 underscore 1? Let me just search it. And 2 underscore. Okay, so good. Let's take this particular example. Uh, this is a particular cell. Now, this is certain part of a leakage power. Forget this thing. Forget in the sense you can see like okay, what will be the leakage power when we are talking about these pins. That means when A equals to 1, B equals to 0, in that particular way, these numbers are there. Then if we are talking about in terms of the area, area in the sense the from the PR boundary point of view, once you are going to design this particular AND gate using a layout, basically the layout, how much area it is going to take. Now here you will see there is no unit. Now, what is the meaning of 6.265? So the way the tool is going to understand, it will just save the default value, and then after that it is going to take these numbers. Then similarly, like leakage power, cell leakage power, we're talking about now. This is the PG pin. So the PG pin, now we are talking about in terms of power ground pins. So what are those power grounds? So in this particular cell, now you can see there is a VGND, VNB. So there are 4 power ground pin, 1, 2, 3, and the 4. And now they are talking about like okay, PG pin, this is the primary ground. This is for your N well, this is for P well, and this is for primary power. So now I'm sure you can easily understand like okay, what we are talking about. So this particular inverter, not the inverter, this particular cell, it will have VDD VSS normal, like we have. So 2 power pins are VDD VSS, and those are related to our normal power. Then there are something which is related to the N well and the P well. So in the N well, P well, they are connecting a different power. Uh, and that particular different power, they are talking about like, okay, this is related to the N well, this is related to the P well. And this is the name, basically, the name is VP bulk. You can say bulk or VPB, just to understand if B is there. And this is VNB, this is with respect to the VN bulk, you can say. So now, so you can see, this is basically logical numbers, logical things are there. So for a tool to understand, this is the format. The way I understood this, so frankly speaking, I opened this particular file first time in front of you, but I can see, because I have a I can visualize it. Look, okay, the way it is structured, and if I can visualize, you can also visualize. Like, okay, this particular AND gate, this is a 2-input AND gate, but in the 2-input, there are the 4 power supplies. Now, what is those power supply? Even I was just like, okay, there are the 2 power supply. Why they are talking about the 4 power supply? Yes, there is a N well, there is a P well, there is a primary ground, primary power, and we all know very well, like, okay, there are the devices like this also, and that's the reason they have just captured it, and they just mention, okay, these are the things. Now, in your design, if you're going to use this AND gate, so let us suppose so in the synthesis, what Aditya mentioned in the morning, so basically they are going to be a circuit, and that particular circuit, you are going to map it with a particular AND gate from the library. So if you're going to do in that particular fashion, think how you're going to choose it. So someone asked, can we optimize in a OSS? No, you cannot. So OSS is not that smart right now, because the open source, it is not going to do the optimization for you. So you have to do the optimization for your design yourself. And you should know, like, okay, how you're mapping, which cell you're mapping with which particular cell. So this is also a 2-input AND gate. Are you going to use this 2-input AND gate? You have, if you know your circuit, if you think you are going to use the power supply in this particular way, then you have to use it. Then you have to map this particular cell with your AND gate. And if you're just using a normal AND gate where the power supply for N well, P well are not different, then what you're going to do, you're not going to map your AND gate with this particular AND gate. So with this particular AND gate, in the sense, the AND gate, your AND gate, in the sense, the AND gate in your circuit, and this is the AND gate in your library. That means your library is characterized with a certain numbers. The moment you're going to map it, your tool is going to do the analysis on the basis of the value present in this particular library. And what value I will show you, like power number, the leakage, and the timing, everything. Tool is not going to do the calculation. A calculation in the sense, tool is not going to do this simulation to figure out what is the delay number, what is the power. Tool is going to directly pick the power number from this particular file. Tool is going to pick the delay value from this particular file. So that means this mapping should be very, very accurate. If this mapping is not good, then your result, your analysis, that is not going to be the accurate one. Any question till this particular place? I think someone just asked a few questions. Let me just see. But I think this point is clear. Like, okay, why there is the importance of this particular part. So someone is saying audio quality very poor. Maybe if is it poor for everyone? Is poor for only one person? What about other people? Are you guys able to listen properly? Not poor, very clear. Okay, so good. So best part is we have a very good sample point right now. So the way I just proved, I just prove it, like, okay, my audio quality is good. That means no problem. So similarly in design also the same thing should be there. Sorry, so it's just like I'm just giving a very bad example, but yes. Okay, so I think no question till now. See, don't go in the integrity of this particular cell. Don't go like, okay, how this cell is designed, why there are 4 power, what is going to be happen. So I'm not I'm not just giving an idea in terms of how the cells are designed. I'm just trying to give you an idea how the files are written and how you can understand those particular files. If you will just open those particular files, it's a readable file. You can easily read. It's the English language. And I know most of you, not the most of you, all of you can understand English. That's the reason you guys are attending this particular session. So if you can understand English, you can read English also. Okay, I think no question. No one is asking any question. Okay, so Zakir, you're just asking again and again. Please demonstrate what what information you need from me in terms of the corners. I'm just explaining that particular part only right now. So if you understand, just focus on this particular part. You will able to understand like what is the different corners we are talking about. Okay, this is a very good question. Surya was asking how to ensure the dot-lib is correct. So again, so the best way, same example, I told you, I just gave an example, 30 minutes to reach from your home to your office or your college. Now, if I will ask you the same question, how can you ensure this 30-minute, which I just gave you, that's the correct answer? That's the correct one. Then you will say like, okay, Puneet, I have to travel. Once I will travel only, then I will come to know whether you gave me the correct number or not. Okay. For that I have to travel. I cannot do anything else. It's the same thing. It's either you have to just travel only, then you will come to know. Else you don't have any other choice. You have to just understand whatever I'm just talking about. Okay. Then in terms of what if my dot lib is not the correct one, someone just screwed up. Means you're gone. If your dot lib is not good, you're gone. You cannot do anything. Okay. Apart from that, someone was asking about, I think my chat window is very. Okay, so one question is, do we need to refer these .lib always to use a particular pin name? Like, yes, because that's the way the layout is there. If in the layout VGDN is not there and you are using in your design, then there is a big mismatch. So when we usually do the LVS, that's the same thing. Like, okay, you are using some other nomenclature, someone else is using some other nomenclature. So for it is very important. Like, okay, you use same nomenclature everywhere. Okay, so that's one question someone asked. Okay, 1 minute. Seeing the questions very easily. Someone is asking about, sir, does the balance tree means the clock tree? No, no. So that's a different thing. I think you become confused. Do these supply voltages or different voltages? Okay, now the question was the worst case is 125 minus 40. What about the best case? Is it always 0 degrees or other? Again, so Naveen, this question is very subjective. Like, okay, worst case is this. What is the best case? I think this is a corner related thing. I will see if I will get the time. I will just explain you that particular part, but not right now. Then someone was asking about we have to perform at least the worst and the best case. Um, yes, at least again it depends. Like, okay, the test, how many test cases, how many analysis you want to do it. Then Chitraja, leakage power of the area, the experimental values. What do you mean the experimental values? Okay, so if you're saying how we have mentioned here in this particular dot.lib files, yes, with a certain experiment, with a certain simulation, we came up with these values. Is it possible to calculate the critical time as we can find in Xilinx? So here basically everything is the on the basis of certain variables, certain conditions, and then the critical time and all those analysis you can do using the prime time or maybe some STA, static timing analysis tool. Someone is asking, NVL is defined the files, sir. Where is the detail information? What detail information you're talking about? Are you talking about the technology related information or the physical related information? Because if you're talking about that, so that's information you will find the technology or the physical uh, related files. You will find that particular part there. Okay, then do these power supplies have a different voltages? Maybe. We don't know. So Ashok, that's a something depends on your design. You want to use these. So these are the pins basically. So in the layout you have, let us suppose you have these 4 pins, like VDD pin is there. Now whether you want to apply on that particular pin, all the pins the same voltage or the different voltage, it depends on you. It depends on the design. That's what the way Foundry just gave you, like, okay, these are the pin. Now you want to use it, you can use it in that particular way. Okay, can you share the information about the minimum and the maximum voltage we can give for operation of this circuit based on the Sky 130? So in this particular case, if you will see, you have the library with the -40, and I think the maximum is 100 degrees Celsius. So that's the range you have in terms of the minimum and maximum. So if you have the libraries with respect to the -40 to the 100, you have to just work on that particular part. So, Zakir, see, I got your point. So again and again, you're asking the same question. The theory you understand, you just want to do the analysis of the on the tool. So let's wait for some time. So definitely, when we are going to do the simulation, when we are going to do the analysis, so I'm going to show you the analysis on the different corners. So analysis, that's what I'm saying. If you know how to do the analysis of a one corner, which definitely we are going to do it, it's just a matter of which particular file you are going to pull. So which particular file you are going to source. If you are going to source a file of a uh, basically typical, that means you're doing the analysis with respect to the typical. If you are sourcing a file with respect to the fast, that means you're going to do the analysis with respect to the fast. And just wait for that particular part when we are going to do this the synthesis, the prime time, that's timing analysis, then some file we are going to use for sure. And whatever that particular file, that means we are going to use that particular corner, that particular conditions. Second one, if you want to do, let us suppose if we will not we are not doing that particular part, then you can source second file and you can do the same analysis, you will get some result. So we will do it, don't worry. Then people are asking about the corner analysis. Okay, I think now you got the point. The corner analysis. Corner analysis in the sense, if I'm saying the timing analysis in the sense, I'm trying to do the calculations for the timing. Now in that particular case, if I'm using a particular corner file, then I will say corner analysis for that particular corner analysis. Okay, okay, lookup tables. I will just show you, then I will just talk to you about the lookup tables. Then I think I'm almost all the people have the almost the same kind of questions. Okay, last question. Who write these .lib files? Uh, who write these .lib files? Simple answer, tool write these .lib files. Now question come, how the tool is going to write these .lib files. Once you are going to do the simulation, after that you will get the certain data. So on the basis of that, tool is going to write it. Now who's going to do these simulation? Maybe tomorrow, Lakshmi, you can do the simulation. So in the company, in the industry, there are teams, they are doing these simulations, and those after the simulations we write these the tool write or we write these .lib files. So what is there? So it's just like you so think about the process. So the process is schematic is there. So you design your schematic, and that particular schematic give the different input outputs. You will get different. You just give the different inputs. You will get the different outputs. Whatever the output, you are just capturing that particular output in a text format, so that some other tool can understand that particular part. So the best part. So why we have so many files? It's like the next whenever the next tool is going to use it, that tool is just read those text value, else tool has to do the complete simulation, so you're just saving the time of the other tool. That's the reason we have these files. Okay, so before we will go for a 5 minute of break, I just want to show you one more thing, and then we will go we will just take a 5 minute of break. So what I wanted to show you, I just want to show you this portion. So it's a two input file, two input AND gate, and the two input AND gate, we know what is, there is a two input, and that input is a or B. So you remember AND gate, you just draw it and you just mention like your two input and you just say it's a A and the B. Now I just want to draw a diagram and I just want to ask one question to all of you. So this is my AND gate. Then in this AND gate, I have written X, Y, Z. Now my question is, with this diagram, what do you think? What do you think? X is a input, or X, the name is the name of the pin inside this particular AND gate? I think there are two things I'm just trying to highlight here. One is there is a input X, and that input X has a, let us suppose, a 10101. This is the signal which you have applied at a X. At a Y, again you are going to apply 00011. That is the input. Basically X and Y at this particular case, these are the inputs. You are going to apply the input and you will get the certain output. But this X you're going to connect with a certain pin of your AND gate. Now, what is that pin? How your tool is going to be understand this X is going to be connected which particular input, which particular pin. Whether now you cannot tell the tool like, okay, connected to the top one, connected with the bottom one, because in your diagram you can easily say like, okay, this is the top one. So if we will talk about this, you can say like, okay, this is a top one and this is a bottom one. You can say in that particular way, or the first one, second one, but the layout in the shape, there is nothing as a top and the bottom. Everything is just like there are the two pins. So you have to write a file, or you have to tell your tool like, okay, you're going to connect your X with a particular pin, and that pin is going to be defined by something. Now, if I will say I'm going to connect X with a pin U, now the question comes, where is a U pin? Where is a pin U? There is no pin U in this particular scenario. And how you will come to know, how the tool will come to know, because the person who have designed a layout, they gave the name of the pin, and that name of the pin, they gave it and they mention it, okay, A. So everything is going to be happen with respect to the A. Now, if I will ask you, like, okay, where is the A? You don't know which one is the A. So in the layout, physically in the layout, the A is going to be defined somewhere. Out of these two, somewhere A is going to be defined. And maybe they have defined in a fashion like, okay, they may be saying like, okay, this is my A. This is my A and this is my B. So maybe you may be thinking like, okay, this is going to be A and this is going to be B. But the way I have just captured it here, this is A and this is B. So now X is not connected with the A. X is going to be connected with the B. Y is going to be connected with the A. And please, it's my request, don't ask me like, okay, does it matter if I'm going to connect X with the A or the B, because both A and B pin both are going to be the same. It's not like that both are going to be same, both are going to be different. So don't be confused like, okay, both the pins are going to be same, and whether we will assign with the A or whether we will assign with the B, it doesn't matter. It matters a lot, because if we are talking about a AND gate, so I'm not going to teach you right now the CMOS related thing, but just to draw a two input one portion of a let us suppose if I'm saying these are the series uh, NMOS, and this is a ground, here it is a output and some pull up network is there. Then if I'm saying this is A and this is B, you cannot say if I will interchange A and B, you will get the same performance. Now I'm not talking about the same output. So functional logically, maybe you can say logically in the sense 1100, you can say in that particular way, like, okay, if even if I will replace A with the B, uh, then you will get the same output. Logically, you can say you will get the same output. But when it comes to the in terms of the voltage, in terms of the delay, in terms of the current, things are going to be changed. Things are going to be changed if you will just change this particular part. So this is very important for us to understand, like, okay, where exactly A is defined. Now from this particular file, it is very difficult for you to figure out where exactly is the A, because this particular file is not going to give you the physical information about A pin. It is going to give you the logical information, functional information about the A. But so for the physical, you have to go and you have to just check the physical file. But from here, you will come to know, the tool will come to know if the something is connected with the A pin, then what is going to be the different values. If it is going to be connected with the B pin, then what is going to be the different values. Now what are those values in terms of the power, in terms of the timing. So this particular file is going to capture that particular power and the timing. Okay, that's all for now. Just take a 5 minute of break, then we will come back and then we will discuss other things. So right now it is 1:16. We will connect in a 1:21. Okay, everyone. Great. Just take a just break. That's all. Small break.
So dear participants, the session will resume from 1:21 p.m. Please don't log out. Hold on. Thank you.
Okay, so I'm back. Well, in the sense I was already here. I think all of you are back. Think so. Okay. Okay, so someone was asking, okay, not the someone, Naveen was asking, sir, I mean, you want to say the X is connected to the A and the Y is connected to the B, and if I reverse it, then VLSI matrix will change. Yes, everything is going to be changed. It's just like there are two sections in your college, section A and the section B. And if I will connect you with the section A, then maybe the class teacher is different, the students are different, the way the section behaves, that's the different. And if I will connect you with the section B, then things are going to be different, whatever the difference, but they're going to be some difference. So it's not only about the whole year you have to complete a particular course, but things are going to be different. It's the same thing. So now let's come back and let's discuss about at least this A and the B pin and the Y pin. Maybe we will just discuss this thing dot lib, so it will give you an idea, because we have already discussed a lot about the dot lib. Initially, I was thinking like, okay, I will discuss this dot lib till I will discuss this dot lib later on, but let's finish this particular part today itself. Before that, just one question, Firoza ma'am. So today we are going to finish this session by 2 or 2:30. I missed that particular part.
Uh, yeah, the timing is up to 2:30
Okay,
p.m.
great. Okay, great. That means I have 1 hour. Okay, I will do it. So yes, so let's talk about this pin A. Now, what is a pin A? So in that particular AND gate, which we just visualize it. So from the timing related information, if I will talk about, or from the power related information, or from the modeling point of view, so what we are doing, we are just trying to model that particular AND gate in a language which tool can understand. So till now we are just discussing that particular part. So when we are doing the modeling, and in that particular modeling, we are talking about like, okay, we want to make sure any other tool any other tool, they should understand this AND gate. They can for them, they are not supposed to redo all the simulation to figure out what is the power, what is the capacitance, and all those things. So what we are doing in this particular file, we are just capturing all those information. So that means in a pin A, what is the capacitance? So if you will just write it here, any other tool, any tool basically, if they have to do certain calculation based on the capacitance, they can do the calculations. So now they know what is the capacitance. Now, if you will ask me like, okay, from where we have calculated this capacitance? So yes, so for this particular value, obviously you are going to have a physical in the sense they're going to be the layout, and that particular layout they're going to be certain layers, and in that particular layers you're going to do the extraction, parasitic extraction. That means you're going to extract the R and the C, and then you will see like, okay, this is the C, this is the capacitance, because the capacitance is going to have a dependency over a lot of things, what layers we are talking about, and in that particular layer, uh, uh, basically what is the weight, what are the surrounding parameters. So that's a part of basically the parasitic extractions, the parasitics. So like in the books you have studied about CGD, CGS, all these things you have discussed. So similarly, this A is basically the gate of a NMOS. If we are talking about the gate of a NMOS, this A is also connected with the gate of a PMOS. So this is a for the A, so that means it will have certain capacitance. And then theoretically, if you will ask me, then you have to calculate. Uh, so you have to calculate basically gate to source, gate to drain for the PMOS, NMOS, and maybe if you have other things, you have to calculate those things. But practically, there should be a layout. You should know what is the thickness, what is the layer, what is the width, what is the surrounding dielectric, all those things you should know, and then only you will come to know what is the capacitance value. So this is that particular capacitance I'm talking about. Then we are talking about, is it a clock pin? No. What is the direction? How the tool will come to know it is the input and output? Yes. So this is the direction. What is the fall capacitance? When the waveform is falling, is your capacitance going to be different or is this going to be the same? If it is the same, you can just write the same value. If it is a different, you can just write the different value. Now you can ask me like, okay, how can the capacitance can change for the falling waveform, the rising waveform? So I think that's a question I'm supposed to ask you. If you're going to apply a falling waveform or the rising waveform, then how your capacitive value is going to be changed. So that's something we are going to mention here. Then the internal power. So now we are not talking about the external power. Now we are talking about the internal power. In that particular internal power, we are talking about the two powers, the fall power and the rise power. Again, this rise power, fall power. When the waveform is rising, when the waveform is falling, at that particular time, what is the power number? Now here, this is very important how things are mapping with each other. So here you can see fall power you are talking about. Now here I've just mentioned power input 1, power input 1, and then you can see the index 1. So just for your record, just see this line is 36713. Let me go at the top, power input 1. So you remember somewhere here in the starting, we have discussed about the power input 1. So here, see power input 1 and with a variable 1. So that means we are talking about this particular lookup template. So this is that lookup template which they have referred at that particular location, and that was power input 1, the same template. In that particular variable 1, they just mentioned the index 1. What is that index 1? It is a input transition time. So on the basis of the input transition time, they were defining the power numbers. So we were somewhere here. Yes. So now here you can see power input 1. This is the index 1. That means the input transition time. So how the tool is going to read, how I can understand in this particular way. In a fall power, that means when the waveform was falling, when you have applied a signal at a which is falling in nature. Now in that particular falling in nature, we are referring a lookup table. In that, what is the name of the lookup table? It's the power input 1. In that lookup table, this is a transition time. So that means all these numbers are the transition time. So this and this is the value. So that means when the transition time is this, then your value is this. And value of what? Value of the power. Transition time is something else. Your power has changed. Transition time, power has changed. That means when the tool is going to do the analysis of the power, it will in a circuit. Now I'm not talking in terms of in your cell. So you did the simulation. So yesterday you did the simulation in terms of the rising waveform. Okay. Now in that particular rising waveform, that means in an inverter, if you will just give a rising waveform, and then we were just trying to calculate the maybe the delay or the output waveform. Now what about the slope? What is the transition time? What about the slope of that particular waveform? If you're going to change the slope of your waveform, definitely your timing numbers and your power both are going to be changed, because in the calculation itself, if you will just go open a standard sum book, then you will see the power has a dependency. The power has a dependency over the transition time, that is the slope, that is it. If you will say some tr, tf, those variables are going to be written in the formula. It's the same thing. But now we are not writing the equation here, because if we will write the equation, even in that particular case, tool can do the calculation, but obviously it is going to take a lot of time. So what we are doing with the help of the lookup tables, we are giving a value, we are giving a scenario like, okay, from this transition time to this transition time, we took a spectrum, we said like, okay, 0.01 to 5.0 is a big transition time we are talking about. Within that particular transition time, these are my power numbers. Now it's very fast for a tool to do the analysis. Now, if anything which is in between these two, so you can ask me like, okay, 0.01 is okay, 0.028 is okay. What about if my transition time is 0.015? In that particular case, the tool is going to do the interpolation. Go type on a Google what is the interpolation formula. You will come to know what is the interpolation. It is just like mathematics coordinate geometry, x1 y1, x2 y2, and the x3 y3. And if you have to calculate the x3 y3, how you are going to calculate with the help of x1 y1, x2 y2, you are going to calculate your slope, and on the basis of that you can if you have x3 you can calculate the y3. It's the same pattern we usually do this interpolation thing. And if you are going to say like, okay, I want to calculate something outside this, then it's going to be the extrapolation. So there are two things. One is the interpolation, another thing is the extrapolation. So those things usually happen when we are going to calculate, when we in the sense the tool is going to do the certain calculation on the basis of this particular table. So this is the importance of the lookup table. Here the lookup table is with respect to the fall power. Similarly, the lookup table is with respect to the rise power. You will see in a below. Similarly, we will have a complex lookup tables also and the easy lookup tables also. But this is the way the tool is going to work out. And from where these value came, someone did the simulation and they captured these value and they just uh, write out. They write out these particular value. So that's the way we usually come up with this number. So whatever the simulation you did yesterday, on the basis of that, you can also create a matrix. It's the same thing like in a college days, we were creating a experimental, I would say that what is that? Lab reports. Yes, lab reports we were creating. It's just like different input values and you just capture the different output values, and there it is like in the form of the table itself. So same thing, but now that table you have converted into in a particular file, and you just gave that particular table a capture in a particular syntax, so it become your lookup table. Okay, now let me just see few of you have are asking some question. What if I made some changes in the some parameter in the particular cell in the dot lib? Suppose I change the rise fall time or the leakage power or some related parameter of the capacitance. Will my design reflect changes? Ankit, yes. Answer is yes. Your design is going to reflect the changes. So now this lookup table, you did the simulation as per the simulation. This was your value. That is after doing the simulation. Now what you did, you changed the value here in this particular file. You change this value. You just mention like, okay, this is 1638. In place of that, you just write it as a let us suppose you just write it as a 2. Just write it 2. Here it is 163. It is okay, but here you just write it 2. So tool don't know. Tool will think like, okay, whatever you have written, that is the correct one. And tool do the analysis. Now, maybe your value will come correct, wrong, because it's just a mathematics. Later on, it's just a formula. On the basis of that particular formula, tool is going to do certain numbers. Maybe that numbers are not obvious. Maybe you were thinking like, okay, how it is coming in this particular way. That is okay. But if you are going to make any changes here, it is going to affect your analysis of your chip. And if your analysis of the chip is wrong, because you change here, obviously the analysis is wrong, then in the real time your chip is not going to work properly, because you did the wrong analysis. And that's usually happen. It's like if someone is going to change these files, you messed up, you're just messing up everything. Naveen was asking about pin A parameters are different, pin B parameters has different. We can see, we will see basically. Why is it so? Physical pin should be have the same characteristics according to me. So Naveen, that's the reason I have mentioned. Go and just draw a layout and just see whether the physical locations are same or not. Logically, you can say yes, they can give in the same way, but the physically the things are different. You will see a lot of things are going to be different. And I think as the prerequisite of this particular course was like you should know at least the CMOS. But okay, since you have raised this question, let me just tell you. So this is my just one thing. Now here maybe you may be thinking like, okay, how the physically it is different. Now the physically it is different. For this MOS, this pin is basically the ground, and here this is not a ground pin. Another thing is, if you know, there is a bulb connection. There is a bulb connection here also. Now this bulb connection, are you connecting with it to the ground or you're doing something else? So you have to understand that particular part. Are you connecting it with the, like you just did it and then maybe you were just doing it like this, or maybe you're just connecting with the ground. So if you will see your layout, if you will see physically, if you will see the characteristics of A and the B, both are different. In this particular scenario, if it is connected with the ground, so I think source and the bulb both are on the same potential. But in this particular case, your source and the bulb are not on the same potential. Both are on a different potential because this is ground, but this pin is not on the ground. I think that's good enough for you to understand, like, okay, physically why they will have the different characteristics. Now capacitance is fixed for the MOSFET level if vary with the voltage. I think again you have to just go back and just check the MOS part. I gave an idea about those things. Charging, discharging, I think that is also okay. Capacitance may charge due to the load good. Does this kind of lookup table is possible at the transistor level instead of using any PDK model files here? Okay, so Chitraja, I didn't get your point. You're saying that this kind of lookup table is possible at transistor level instead of using any PDK model file. So basically, okay, so transistor level also you can create the similar lookup tables. So this is coming from the transistor modeling. Basically, you in place what you have done, you have used that particular transistor. You did the certain modeling. On the basis of that, you came up with this these type of numbers. Here we are talking with respect to the cell. Now you can say like, okay, now you want to do in only for the NMOS or for the CMOS, sorry, NMOS or the PMOS. Then you're talking about the BSIM models. So that models are there, those things are there. But there obviously it is not going to be the lookup tables, but the numbers are there, variables are there. So things are there basically, I would say. I think if that's something you want to ask me. Okay, now let's try to understand the lookup tables. I think if all of you understood this particular part in terms of the lookup tables, then let's see the other thing. Here they are talking about the related pin, ground pin, power pin, maximum transition, rise capacitance. Now if you will see the B pin, now they are talking about the similar thing on the B pin also. Now one thing maybe I can just show you here. Now see, it's very clear. I think now I'm just trying to, sorry. Did some, yeah. Looks like I just messed up something. Wait a minute. So it is and do underscore, but I think here only, yes. So we were talking about, yeah, not the axe, yeah, this one. Sorry guys. So what I just want to show you, I want to show you the fall power. I just want to show you the fall power of A and the B. So now here you can see, I think this is the best example for you to understand. There are two pins of a two input AND gate. This is the fall power. This is the fall power of B. This is the fall power of A. Now see the index transition time. We are applying the same transition time on a fall power on a and a B. Now you can you guys see the value? This value. In case of a B, it is a 00130, 0.00130. In case of a, it is a 0.00145. I think now all of you should be able to understand why we were talking about the two different matrices, why we are talking about the two different lookup tables, why we have a two different section for the A and the B. Physically, in terms of the equation wise, in terms of the MOS wise, transistor wise, I gave an idea like, okay, in a MOS, how these things are different, how these things are placed different, and how these, if you will just go back and just do the calculation, then you will come to know like, okay, there are the different numbers. But that's the something you have to refer every time your book and you have to do the calculation. But if you do the calculation and if you come up like, okay, for this particular transition time at A, this is your number. And if you're going to do the same transition, if you're going to apply here, your power number is this. So you just you just capture that particular part and just give it to me. I'm not going to do that particular exercise again and again because I believe in you, like, okay, you have done the great job. So that's in front of you, internal power, fall power, for two same type of pins. So maybe for you it's the same type of pin, but if you will see from the value point of view, the numbers are different. So that's the reason we usually have two different sections, and these numbers are there. And now when the X you're going to connect with the A or X you're going to connect with the B, you will get the different results in terms of the powers. And it is very important, like, okay, in a design, you will see people are talking about like, okay, X you have connected with the A or X you have connected with the B. Sometimes you will fix certain issues just by interchanging interchanging this pin. That means in place of connecting X with the A, you just connect with the Y with the B, and you will see like, okay, your results are different. Why the results are different? Because when results are different because of this particular file, and from where this particular file came, someone did this simulation and they just write out this particular file for your ease, like you can just do the work properly. So from the research point of view, because most of you guys are research scholars in the colleges, I'm 100% sure if you're going to do all these analysis, you can easily figure out like, okay, what is my result, and you can just see this particular part here. Now this is the B. Now we will have certain thing which is related to the X. X is basically the output. So in this particular case, our output was X. So A, B, and X. Now in the X, I will just show you the internal power because we have discussed about this particular thing. For the timing, maybe I will come back later on. I will just show you, but little bit I will just show you here. Now here they are talking about the power pin, and they are sorry, fall power, they are talking about the rise power. But here if you will see, they are also talking about the related pin A, like, okay, which pin is related. So we will discuss that thing some other time. But for the X, or maybe I can just tell you right now just to give you an idea. Yes, so basically for the X there are two pins, two input pins. So there can be the two different numbers in terms of the delay when it comes to A to Y. Any signal if you have applied a signal at a pin and that is affecting the Y. So that basically we usually talk about in terms of the arc, power arc or the timing arc, input to output relationship. So here we are talking about the related pin A. That means when you are going to apply a signal at A, how your output pin is going to be going to behave. It is related to that particular part. That's the reason we are talking about the related pin A. That means you are going to make certain changes at a pin A. That means changes that maybe it is like rising or the falling, and then how the output pin, which is a X, is going to behave. So in this particular case, we are doing this power thing. So we will just do, we will just capture that particular number. Similarly, if you want to capture it with respect to the B, then you can see there is a related pin by B, and then we are doing the similar type of analysis, and we will just tell in that particular fashion. And here also you can see the numbers are different. So here these numbers are different. Now what is this index A1, index 2? For that you have to just go and you have to just check power output 1 in the lookup table at the topmost where the template was there. What is the index 1, index 2? And on the basis of that you can figure out like, okay, what is this particular matrix? So it's some matrix of I think 5 cross 5 or the 7 cross 7 matrix is there. 3, 3, 6. Yeah, it is a 7 cross 7 matrix. And what are those variables? You can go, you can just check that particular box. Means tool is going to do that thing, but that's the exercise for you. You can just do those things yourself. Now, this is all about the power. Now, similarly, we will have similar type of thing on the timing also. So the timing, now we are talking about what if you're going to apply the falling waveform, what if you're going to apply the rising waveform. So in the timing, there are two information we need. One is the delay. That means input to output delay. And the second thing is a transition time. So just for now, just remember this thing. For a particular cell, you need two information from this cell. One is the delay and another is the output transition time. And these two things, cell delay and the cell output transition time, they have dependency over the input, and they have the different values with respect to the pin A, with respect to the pin B. And that all that dependency we are capturing here in the form of a matrix. So when it is a falling, then what is going to be happen? When it is rising, then what is going to be happen? This is with respect to the delay. This is a transition, output transition, fall transition, and rise transition. And obviously all these four matrices with respect to the pin A, and similar type of matrices you will see with respect to the related pin B. So that's all and done. This cell information is finished. So if you will ask me like, okay, what is there in a dot lib? So this is the information which is present in the dot lib. In the dot lib, it is present the your power information, timing information. I gave you a good idea about from the syntax point of view. I think what you guys should do now, just open a .lib file, any .lib file, identify a cell. This is a cell, and now try to understand the uh, different portion of that particular cell. This is a AND gate, logical cell like AND gate, NAND gate. So it's very easy for you. That's the reason I just capture that particular part. Similarly, if you're going to pick a cell which is related to the basically the in the library, you will have the flip-flop also. You may have the AOI and or inverter. That is also can be considered as a cell. And those all those information, the power, the timing, all those things will be there. So this .lib is basically now when we were talking about the standard cell. So these are basically the standard cell which you can use in your design as it is. If you are talking about the macros, you can use all these. So you can have a .lib for your macros also in a similar fashion. There are input pins, there are output pins. And with respect to the input output pins, you can have the power relationship. Similarly, you can have the timing relationship, and accordingly, you will have the numbers like power numbers and timing numbers. And then once you have this particular .lib, you don't need to understand how the circuit is there inside that particular cell. So here you just know like, okay, how the numbers are there, how the timing numbers are there, how the power numbers are there. You don't know, but just by seeing this particular file, you don't know whether A is connected. So basically, what is the physical location of A? What is the physical location of a the transistor associated with the A transistor, A pin, or the transistor associated with the B pin? You don't need to know all those things, at least in this particular file. So it is considered as a logical file, logical information. All the logical analysis like power, timing, you can do with the help of this particular file. If you have to do the area analysis, then you need a area related file. Okay. So I think this is all about the .lib logical files. Any question? Any question you guys can ask right now? No question? You guys are there? Just say yes or no. Okay. Ankit is there. Only one person. That's all. Okay. So is this clear to all of you guys? Or yes or no? So the reason I'm spending so much of time just to explaining all of you guys, because this is the area where most of the people they lack, and they don't understand this particular part also. And if they will not understand, it's very, very difficult for you guys in a long run to do a RTL2GDS thing. And when we are talking about the research scholars, when we are talking about the educational institute, if you don't know this particular part, it's very, very difficult for do I would say frankly the research. Okay, great. So people are listening, people are answering. Okay, so someone was asking if, sir, if three parameters, how to choose the value of power? Okay, so I didn't get it. So if you are saying if it is a three parameter, okay. So if you are saying the power has a dependency of the three parameters, then it's going to be the matrix accordingly. So right now so you have to just write it. So right now we are talking about in terms of the two parameters. It is a two index. So you have a matrix, two-dimensional matrix, then is going to be the three-dimensional matrix. And now how you're going to represent that three-dimensional matrix? So usually what people do, because matrix in our case we have to just write it. So what they do, so they have interdependent matrices. That means one matrix and the second matrix. So with the help of the two variables, they will have a one matrix. With the help of a third variable, they will have a another matrix. And then that means they are just converting the 3D matrix into a 2D matrix. And then rest of the places you have to do the interpolation. So people do in that particular way. So there are not basically in the .lib. Yes, not in the .lib, but there are some other lookup tables when it comes to the foundry specific information, where we are talking about the parasitics and all those things, because there the dependency or the not only the three parameters and the four and the five variables are also there. And the sequence is like, first you just do the calculation on the basis of one matrix, then whatever the result of the first matrix you're going to apply, and you will do the analysis. You will just check, figure out, extract the value from the second matrix, then whatever the result of the second matrix, on the basis of that you will apply that value on the third matrix, and you just calculate the final value. So people are doing a lot of things, so you can do everything basically. So now someone is asking, power is calculated based on the value in that position. Yes. So it's like whatever is written here, if you're giving this particular file, .lib file, to your tool, the power information, the timing information is going to be calculated on these values. If you're going to change these values, your final results are going to change. Now, if these values are different in a different corners, obviously these values are going to be different in different corners. When I'm saying the corners, that means different temperature, voltage, and the process related value. That means when you are doing the analysis, with the using one set of file, one file, you will have some value. That means you are doing the analysis with respect to that particular value, that particular file. Now, if you will change the input file, that means you are doing the analysis with respect to the second file. And that second file is, if there's a second corner, you're doing the analysis with respect to the second corner. So that's the reason. If you remember, I just draw a diagram where there were the four corners, and I was just talking about if you just cover all these four corners, if you satisfy your chip, like your chip is working all these four corners, then your chip is going to be work very well in all the other corners, which is covering those four, all the other scenarios. So same thing is happening, like how you're going to make sure like, okay, your chip is working for those four corners. Yes, using four different files, you're going to check and you will just see it. And I will show you. I will show you in one of the with the help of the tool, like okay, how you're going to do the analysis, and in that particular analysis, what numbers I'm talking about. But I think by now you guys are clear from where the tool is going to pick the values. If you're going to have the two different files, these values are going to be different. If the values are different, your analysis is going to be different. I think that those portions are clear. And if you're going to manually change the value, then definitely your analysis is going to be different. Okay, now all the things you have discussed now related to the Sky 130 PDK, which is a technology related parameter, maybe the MOSFET, the BJT technology. However, why this PDK is having information about different standard cell, why this PDK is having information about different standard cell. Okay, Wasim. So now let's talk about this particular question. So he, if I understood his question properly, so it's all about, we are talking about the different standard cells. So there is a Sky PDK, it's a process design kit. That process design kit is basically the technology file. They came up with a certain things. Now he's saying, he was asking like, okay, how this information is present with the different standard cells. So it is present because they created a standard cell. That means they the schematic, the layout, then they did the simulation. After the simulation, they created the different dot lips in a different corners. And for you to work, to do the research or whatever the project you want to do it, they provided you this thing as a part of a the PDK. You can, what you can do now. Let's talk about for you what you can do. Come up with a new cell. You can come up with a new cell in the sense with a new type of a cell with the PMOS, NMOS. Maybe we will not talk about the AND gate, NAND gate. Maybe you can say like, okay, A bar B. Let's take an example, A bar B. Schematic, maybe you can draw the A bar B, the layout also. For the schematic, do the simulation, create the similar kind of a file, and or you can say for the A bar B, you can come up with the .lib file. So now that .lib file will have the definition of A bar B and all the similar type of matrix and all other things. So that becomes the .lib of your cell. So if you have a custom cell, now that's the difference. If you're going to use a custom cell, you will have your own .lib. If you're going to use a standard cell in the sense, it has a certain standard numbers in terms of the height of the standard cell. Usually we define in that particular way and the track of these standard cells. So those are again the different area. But on the basis of that, they have shared with you like, okay, this cell, these are the numbers. Okay, so then Ankit was asking what is the key difference with the FFSS lib file. Ankit, frankly speaking, now I am expecting you guys just to go and open a file and just see what is the difference. So there are two type of difference. One is conceptually, what is the difference? I think conceptually I have already shared with you what is the difference in the fast, slow. Fast in the sense NMOS, PMOS both are fast, slow. That means NMOS, PMOS both are slow. Now let's talk about in terms of the values, in terms of the numbers, because conceptually is okay. But what are the key differences like you just asked me? In terms of the power, numbers are different, timing numbers are different. If I'm saying fast, if I'm saying it is a fast from the timing perspective, go and just open the file and just check it. The delay numbers are less or the delay numbers are more. If the delay numbers are less, that means that is a fast. If the delay number are more, that means it's a slow. See, I will just see, I can tell you each and everything, but that's not the way you're going to learn it. Go, just open these files and just see, just explore this particular part. That's the reason I'm spending so much of time with you guys. Now then, dynamic and the leakage power from the number value given the library file. I think first you have to understand what is the dynamic leakage, how you're going to calculate it, and then you can do it. I think I'm not supposed to tell all these particular part. Power calculation are made on the values on this position. What does it mean? The power calculation. Yeah, I think I just asked. If the design is the area concern, which file we refer for that? Okay, so this is a good question. Now the question is, if it is a area related, which file we refer for that? So Vishnu, I think, yeah, Vishnu Vardhan. So Vishnu, try to understand what do you mean by that area concern. That means you want to optimize the area. If you want to optimize the area, you want to pick a cell which is small in size. Am I right? That's something your expectation. Okay, the AND gate can be of different size. You want to optimize the area, so you're going to pick a AND gate which is smaller in size. Now, if that is your concern area, then whatever the power and the timing, that is not your thing. Like, you have to trade off. Maybe the small one may not have the power number, the timing number which you were expecting. Just so from this .lib file, if you remember, there is a one parameter at the top which is written like as a somewhere here. If you will see, yeah, this area cell front cell this area basically. So this is going to give an idea which particular cell have a smaller in size, which particular cell has a bigger in size. So if it is a you're talking about right now the optimization. So, and I've just mentioned in the starting itself that the free open source tools, optimization is basically based on a lot of algorithm, and somehow these tools are not so smart. They can optimize each and everything, and that is again you may be thinking from the because if you want to optimize the area, there are there are number of ways. So right now I'm just saying, first you have to optimize your circuit. Within that circuit, if you think everything is good, then with the help of this particular parameter, you can map your AND gate with respect to with respect to the AND gate which is present in this library, which is less in area, and you can do that particular part. I think now it should be clear. So if you are doing it optimization with respect to that, that is the one way. If you are doing the power optimization, now power optimization, it's not a single value. Maybe in one case the power is coming in a higher side, and another is another side. So when you are doing the optimization with respect to the power, manually how you are going to do it, you are going to map your schematic cell with one of these cell present in this particular library. You're going to do the power analysis. Then you will see, okay, what is the power number. Then you are going to map your cell schematic cell with some other cell which is present in this .lib file, and then you will see what is the final power number, because after the analysis you will come to know. Now whatever is coming on the lower side, that means that's a power optimized number. Similarly for the timing also, you are going to do in that particular way. So the point is, in this .lib, someone provided you this .lib with the library with the different numbers with the different conditions. Like someone there, let us suppose for the AND gate there are 10 different type of AND gates, and those 10 different type of AND gates in terms of different in the sense they can be different in terms of the area, they can be in terms of different in terms of the power in the sense uh, the physically maybe they have a bigger width, or maybe they have a different structure, maybe they have some different supply, or maybe they have the different range of characterization. So there are different values of powers in a AND gate. So there are, in this particular way, there are different 10 type of different AND gate, and then you yourself has to optimize your design. You have to just map it manually one by one. You have to see it like, okay, which one is going to suit, which one is going to work as per your specification, and that's what the tool is doing. So if they are good in optimization, you just tell them, look, okay, these are the 5 libraries, these are the, inside these 5 libraries, every library has the 10 cells, that means the 50 cells we are talking about, and you will just run a single command. You just say like, okay, optimize it and just give me the final result, and it will optimize it. It will do all these things for you, and it will give you a final one, like, okay, if you want to do the timing optimization, then you should map your cell with respect to this, but you should map this cell with this cell. If you are going to do the area optimization, then you have to map like this. If you are doing the power optimization, you have to do in this particular fashion, and maybe so you can get everything with a single number also, or you can get everything with a different 3 different cells also. So that's the thing people are doing. Okay, someone was saying I'm returning sheets. My name is written against someone else. Okay, I think Edwin, this is something you can talk to the AICT team directly. I cannot comment on this. Okay. Then there is a generic question, or a more generic question: is any frequency related information captured in the lib? Yes. So frequency related information is also captured in the lib, depending upon your cell, if that cell has certain frequency related thing. So there are a lot of information is captured in the dot lib, depending upon the type of a cell the cell is going to be operate. Like right now we are not talking about the clock, but sequential cells, they they are more or less about the clock related. Let me see if it is there, then maybe I can just show you something. Yeah, so this is the flip-flop. So if this is in this particular file, this is something, I think some flip-flop. This is a D flip-flop. So what I will suggest, you just go and just check it. Like, okay, these are the power numbers with the rest of the different pins. Now here, if I will talk about the pin, how many pins are there? So you can see the C pin. So there is a clock pin CLKN. Then there is a something with respect to the pin D. Then there is a something with respect to the pin Q. Then let's see if there is any other pin. Okay, the pin Q is the output pin. Oh, great. Then there is a pin QN, so negative QN. So point is, any cell, any complex cell, any easy cell. See here, you have the reset B also, and then if the reset you have, then set you have the set also, and everything have a different things. They will have the rise constraint. They will have the other parameters. So is for me, it is very difficult to give an idea about each and everything. But yes, whatever is mentioned here for the lib, it is the IEEE standard. If you will go and just on a Google, just write lib syntax IEEE, then definitely you will get a IEEE standard lib file. Not the file, that manual, where if you just download it, just try to understand what is the meaning of a related pin, what is the meaning of the timing, what is the meaning of a fall constraint. Everything they have specified, they have mentioned there, and it's very easy for all of you guys to understand if you have a little bit understanding about the different different things, and it's written like this. See, if you just write it, if you just read it, you can understand minimum pulse width. So they are talking about something minimal pulse width. There may be something like here they were talking about the run LVL, what is 5 and accurate. I will say like, okay, this is something related to the simulation thing. Forget it. At least 90% of the syntax you can understand just by reading that particular file. Okay, I think, okay, that's good. Okay, now let's come back here. I will just finish this particular left def also, and then maybe for the day we will just finish it for at least for today. So now let's talk about physical libraries. So like I said, it is it will have the physical related information. So there are two formats which we are using, LEF and the DEF, library exchange format, design exchange format. Just give you a very small idea about what is the LEF and the DEF. So in the LEF, if you will see, there is basically we are talking about, okay, so before that, let's try to understand what is going to be there in the LEF and DEF. Or in terms of the syntax, because if you have to understand first, you have to understand from the syntax point of view. So if you will see here, so there are something is written site, there is written as the core. So basically here we are talking about the core size. So this is the core size. IOX, IOY. So here we are talking about the for the X direction, input output X direction. This is the size we are talking about. So that means we are talking about the pad 37.8 by 444. That means some numbers will come here. Now, so here you can see we are talking in terms of the numbers. We are talking in terms of the size. We are talking in terms of the width, length. We are talking in that particular way. So this is the one way we are representing like the square block or I2 block, L block, corner. Everything is they have just mentioned like, okay, what is the thing. Then if there is a specific macro, and like in that particular macro, how they are going to define a particular layer. So physically, if I will ask you like, okay, you have to visualize, not the visualize. So there is a picture, and if I will just ask you just to write the picture in a text format. So you will say like, okay, in this particular picture, there is a layer. There are 5 layers. Okay, done. There are 5 layers. Now, what type of layers? Those are rectangle in shape. Okay, great. Those are the rectangle in shape. Okay, how those layers are, what is the, so how you're going to represent a rectangle? The question comes, how you're going to represent that particular rectangle? You will say, I want to represent that rectangle in the form of length and the width. Okay, I'm okay with that. Like, okay, you just represent that particular rectangle in the length and the width. Or maybe you will say like, okay, I don't want to represent that rectangle in the length and the width, because then the question come how I'm going to represent it in a form. So basically, let us suppose this is your some design or standard cell, and here this is your layer. And if I will ask you just represent this thing. Now, if you will represent me with respect to the length and the width, then you have to also tell me like, okay, Puneet, in the big picture, this layer is supposed to be here only. That means it should start from this particular position. It should start from here. Because if you will just give me only the width and the length, then what I'm going to do? I can draw this rectangle anywhere. Maybe I can just draw everything here. Then you will say, no, 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 you cannot do it in this particular way, because it's going to be start from this particular corner. So you are going to tell me like, okay, Puneet, it's going to be start from this particular corner, this particular corner. So if that is the case, so this is not going to work out. So that means if this is the corner, you have to tell me, you have to tell me, okay, this is the big box. In that particular box, let's talk about, this is basically a 0, 0. So then you will say like, okay, Puneet, this is your 0, 0 coordinate. And then you will say like, okay, Puneet, this is the x1, y1 coordinate. This is x2, y2 coordinate. And this is more than sufficient for me just to draw a rectangle. So you have to just tell me like, okay, this is a rectangle. This is the coordinate. This is going to be start from here and then done. Things are going to be, things are going to happen automatically. So same thing I have done. I just captured it here. There is a pin, VDD pin, direction, input pin, and then I just said like, okay, the share is a bitment. I'm going just to, so this is the one syntax. Then we are talking about the port metal layer 1. So this is the layer name, size is the rectangle. This is x1, y1, x2, y2. So 45.8, this is x1, 0 is y1. 55 and the 6, this is x2 and the y2. So that means now we are talking about the coordinates. Now this particular coordinate is within this particular filler cell. Like, okay, this is a filler. The size is 67.2 by 6. Symmetry xy, some angle is given r90. So those things are there. And then there going to be one more definition somewhere we are going to where you are going to talk about the coordinate of this particular filler cell. That means from where it is going to be start, whether it is going to be start in the bigger picture. So that means there is a core. In that particular core, you are saying this is the size of my core. In that particular core, the one top left side, that is a 0 0, if that is the case, and then everything is going to be specified with respect relative to that particular coordinate. So now here I just specify this thing. That means now if you want to place this macro as a top corner somewhere, then you have to just define the starting offset basically, or you can say, I can say the starting coordinate of that particular thing, because inside that particular macro everything is related to the position of this particular macro. So this is the way I'm presenting, writing my file, which is a physical file. I am going to provide to the tool. That means in the form of the coordinates, in the form of the layers, in the form of the layer number, in the form of the layer, the name of the layer. Now question come, M1. What is this M1? Which layer it is? So we will discuss that particular part later on. We will discuss that thing tomorrow. We will discuss that particular part, like, okay, layer M1, what is this layer M1, how the tool will able to understand what is this layer M1, which color it is, or which type of layer it is, how the tool is going to draw this particular M1 layer. Because as such, if you will ask me M1, I don't understand what is this M1, because nowhere there is any definition or anything with respect to the layer number M1. Maybe you can say, okay, this is a cell. Maybe you can just write something related to the macro and you can say like, okay, this AND gate tool can understand. I have defined it in somewhere in a my .lib file. Maybe you can say in that particular way. But inside that, when we are talking about the physical layers, but that physical layer till now we haven't defined anywhere. So how the tool is going to understand, we will discuss that thing, uh, that particular part tomorrow. Now here there are similarly like you can see even the via, and there are some other layers also. Same thing happen in case of a def. Def is also consider the in a same format, almost the same thing. It's just like these two, left and the def, we usually use to bifurcate the information. Like we are just categorizing the information. Like one set of information we are providing in the left, one set of information we are providing in the def. So if you are thinking just by using a def you are good, no, you but just by left you can do everything, no. So at least from the tool point of view, we are using the left and the def both. So that's the reason left and def we are using, the name is as a together. It just at few stages of my design we don't need both the things. Like when we are talking about the floor plan, we usually do the floor plan on the basis of the def aware floor plan. So we need the floor plan in that particular way. So we will discuss that thing in the and the flow itself, like okay, when we are going to discuss that particular part. So just a small thing. I'm not going to discuss this thing in detail. There are two type of left. We categorize it: tech left, cell left, and then it is a abstract view. So like this is your layout, and this is your layout. So if you will ask me, okay, what is the left? So this is the left. This is the abstract view. So you can see lot of files, lot of layers. I have just removed it from here. It has lot of layers. This is something which you have created as a layout. But if for this particular layout, if I need a left, so I will create this particular left. This is the abstract view. And for the from the tool point of view, for the physical tool point of view, or there are certain other things, this much information is sufficient to do the certain analysis. But yes, not for the fabrication point of view. For the fabrication, you have to use this only. But yes, for doing the certain analysis, this is more than sufficient. Now, when we are talking about the tech left, it will have certain technology related information. So tech left in the sense technology left. So this is certain technology related information. Technology in the sense something which is you cannot change or you cannot define. So foundry is going to be defined. So that's the information will be there. Now, like page width, spacing, those information is there. Now, similarly, if we are talking about the cell left, so that I have already discussed the standard cell related thing, the cell name, origin, size, pin name, use of the pin, all those things we are going to define it here. Def is basically when it comes to physical layout, the whole IC. So it's just understand like standard cell related information or the design related information. Now, if you are talking about the design related information, so that comes under the category of the dev. Now it will have the macros, it will have the top level, the pin locations, blockages. Then we are going to talk about like the tracks, the orientation, all those information is also present in the def. Okay, I think that's all for today. We will just stop it here only as such. But yes, if you guys have any questions, then we can discuss and we can close the session here itself. Okay. Now, someone is asking if we can do interpolation, extrapolation, then only 2 time units are sufficient. If I'm getting it right, why we need 6 or the more, etc. Okay, this is a good question, Tiwari ji. This is very good question. So the question is, if we can do the interpolation. So if I have x1, y1, x2, y2, and if I can do the interpolation, in the sense the tool can also do the interpolation, then why we need so many numbers? So that means the 6, 7, 8, or why we need a 7 cross 7 matrix, or anything. Why we need so many numbers in the variable? Just 2 numbers are more than sufficient. So you are 100% right, but there is a one assumption. You just assume in that particular thing, and that is like between x1 and a y1. So we were talking about the slope. That means you're talking about the linear relationship. That means between x1 and y1, everything is a linear. Only then you can do the interpolation. But if it is a non-linear, if it is a curve, or maybe it is for a small distance, it is following a particular slope. After that, the slopes are going to change. Then how you're going to capture it? And if you need a accurate analysis, then there is a concept of a piecewise linear relationship. Piecewise linear relationship in the sense you're going to sample your curve, that particular equation. So see, it's if you want to understand it from the equation point of view, linear equations, non-linear equation, quadratic equations, you know how the curve and the things are there. And if I will ask you like, okay, there is a quadratic equation, there are the 4 or the 5 different parameters, and they have the let us suppose the two information itself, but they have the quadratic relationship. In that particular case, it's very difficult for you to do the interpolation, and if you will do the interpolation, your results are not going to be accurate. So what you're going to do, either you just use the equation as it is and do the simulation, then only you will get the 100% result. But that's is going to take a lot of time. The second thing is you tell the tool, like, okay, see, I'm going to do the simulation for you, but what I'm going to do, I'm going to sample the things, and I'm just making your life very easy. So what you're going to do, you will just sample the things, and on those samples, that means depending upon the number of samples, if you're going to do the 10 samples, your results are going to be more accurate, 20 samples more accurate, if 500 samples more accurate, and if it is just a 2 sample less accurate. So that means numbers which you are talking about, the more numbers, that has a dependency of the accuracy, and it depends on you how you're going to characterize your library, how you're going to do the sampling of your things. I think Tiwari, it should be clear by now. Okay, so okay, what is the antenna effect? Forget it. Just go. Just I think just learn the CMOS, and that see what is the antenna effect, or maybe we can discuss sometime later on. So Rajesh was asking, def and the left is a similar like to store information regarding size, placement, DRC rule, etc. Yes, not the DRC rule, but yes, you're right. I think changing this dot lib is not in the hand of a circuit designer. Oh no, so left and def and the dot lib both are the two different things. Okay. So left and the def, they have the physical information. Dot lib has a logical information. So don't be confused here. You cannot change a left into a dot lib or the def into a dot lib. Both have a different kind of information. Okay. Any other question, guys? It's like maybe you're just listening, but I'm really tired. Anyone? So if you have questions, then ask. Else, okay. So you're saying routing blockage. We will discuss later on. Everything you want me to cover today itself. Okay. Great. Yes, Surya, it's a long day. I know. It's a long day for you also. Great. I think we should end the show now, and we can connect tomorrow. Okay, great. So Firoza ma'am, we are almost done. If you want to make any announcement, please.
Okay, thank you, sir. Thank you, Aditya sir and Puneet sir, both of you, for your excellent presentation on this day 3 of the program. So with this, we come to an end to day 3 of this 10-day long FDP program. So tomorrow we will be joining by 9:30 a.m. So all the participants are requested to be sharp on time. And apart from this, there is one announcement from our end. All the participants are requested to please go through the attendance sheet link which has been web published. Okay, and the link is shared in the announcement page, important announcement Google Doc page in the shared Google Drive link. So from there you will get the link. From that link you can access your attendance sheet, and the attendance sheet is based on the email ID which you have used to log in into the WebEx platform. So in case if you have used any other email IDs for logging into the Cisco WebEx platform for the 2 days, then please note down your email IDs which has been mentioned already in the attendance sheet, and from day 4 onwards please use that email ID only to enter into the WebEx platform, or else your attendance won't be tracked. So we request you to please enter from your registered mail IDs only. So that's it from our end. In case of any problem, any difficulties, you can let us know. So many participants have problems in tracking the attendance sheet. So I am repeating again, the attendance sheet is a Google Doc link which has been web published, and the link is been already uploaded in the Google Doc file named important information in the Google Drive. So in the Google Drive, you need to go into the important announcement page. From there, you will get the Google Sheet link of this attendance sheet. Okay, from that link, you can find out your attendance of 2 days, last 2 days of the program. So today's attendance will be updated tomorrow. So with this, we come to an end. So thank you all. Thank you for joining and cooperating with us in order to complete this day 3 of the program successfully. Thank you all. So we request all the participants to please get disconnected. The meeting will end in next 2 minutes. Thank you all. Thank you, Puneet sir. Thank you, Aditya sir.
Thank you. Thanks a lot.
That's it from us. Thank you. Thank you.